Okay. Hello, everyone. My name is Wang Lei, and I'm very excited to stand here for you to introduce the geotechnical modeling in Opensees. And today, Professor Chu Jian and I will spend the next 2 hours talking the efficient way to use Opensees for simulating the geotechnical engineering problem in Opensees. Okay, we have prepared some numerical examples, and we hope you can find it help and have a good class today. Okay, and and firstly, I want to introduce myself. Okay, I studied my PhD in Xiamen University and graduated in 2021. And during my PhD, I focused on the refined simulation of concrete using Opensees, mainly about the FEM, DEM, coupling method, and paradynamics. And I'm also a developer of Opensees and have studied a little soil defecation and knows how to simulate the geotechnical problem in Opensees. Okay, and in 2018, I was very lucky to go to the University of California, Berkeley as a research scholar. And there I worked with Frank McKenna, who is the major developer of Opensees. I learned a lot from him. And during that time, I developed the response sensitivity analysis framework in Opensees, and also studied paradynamics there and implemented the theory into Opensees. And right now, I work in Wenzhou University and continuing doing my research studied in my PhD. Okay, and today I will talk about the soil foundation structure interaction system in Opensees. And I will introduce how to build the soil, the structure, and the interaction between them. Okay, now let's look at the soil foundation structure interaction system. And I will call it SSI system in the following class. Okay, this is the core SSI system. And you can see a lot of numbers in this figure, right? And the number within the circle indicates the number or the tag of the beam column elements. And the number within the rectangle indicates the number of the soil elements. And the number like this in the plain text indicates the number of the nodes. Okay? And the SSI system can be divided into 3 parts: the frame structure, the soil, and the interaction between the soil and the frame structure. Okay. For the frame structure, we can see that it has 2 stories. For each story, it is 3.6 meters high, and it has 2 spans. Each span has 7 meters wide. Okay. And for the soil, we have 4 layers here. And for the first and the second layer, it is 1.2 meter depth. And for the third and fourth one, it is 2.4 meters depth. Okay? And to simulate the interaction between the structure and the soil, we need to build the piles and foundation at first. The piles are the substructure of the frame. Okay? So we need to build the pile under the node, under the column, right? So we need to build the pile under the node 1, 4, 7, okay? And we take this part as an example. You can see that under the node 7, we build 2 beam columns labeled 16 and 15, right? And the code elements surrounding these 2 beam columns are the foundation, okay? For example, 65, 67, 86, and 85 is one of the foundation elements labeled 65. Okay, to simulate the interaction between the piles and the foundation, we need to connect the node of the pile and the node of the soil. For example, here we tie the node 7 to the node 105 and tie the node 15 to the node 86 and 14 to the 67. The command to connect these two points will be discussed later. Okay, so this is the whole model of the SSI system. And after we build all the model in Opensees, we will apply the gravity load to the of the whole SSI system, and then apply the earthquake acceleration to the base of the soil to do the dynamic analysis. Okay, and then I will introduce you how to build the model in Opensees step by step. Okay, firstly, we need to build the frame structure. And we use this command, this TCO command, to define the node of the beam and column, and also set the lump mass to the node. It is noticed that NDM2 indicates that it is a two-dimensional model, and NDF3 means that for each node it has 3 degrees of freedom. And I will say DOF instead of degree of freedom in the next class. Okay? So the DOF is 3, means for each node it has 2 translation DOF and 1 rotation. Okay? And here we use the set command to create some variable values to store a value, and use the node to create a node in Opensees. And the numbers following the command node indicate the tag of the node, the coordinate in x and y direction. And if we want to set the lump mass to the node, we should use the keyword mass here. And the numbers following the keyword mass indicates the mass in the x, y, and the rotation directions. Okay, so we can use all these commands to define the nodes of the frame of the superstructure of the frame. Okay, and then we can use the similar command node to build the node of the piles. Okay, and also set the lump mass to it. And before we create the beam and column element in Opensees, we should first define some material and the section of the element. So in this model, we use the concrete 01 to simulate the mechanical behavior of the core and cover concrete. Okay, the figure on the right shows the strain and stress relationship of the concrete 01. And from this figure, we can see that the concrete here cannot be tensile because when the strain is larger than 0, the stress is always 0, right? And for the material model here, we have 4 important parameters. For example, epsilon Cu indicates the strain at the crushing stress, and FPCU indicates the crushing stress. Okay, and epsilon CO means the strain at the maximum stress, and the relative stress is called the compressive stress. Okay, and we use different values to simulate the core concrete and the cover concrete. And the values are shown in this table, in this model, okay? And for the steel, we use the hardening material to simulate the mechanical behavior of the reinforcing steel in this model. And the figure on the right shows the strain and the stress relationship. And we have 4 parameters used in this model, which is the elastic modulus, the yield stress, the isotropic hardening modulus, and the kinematic hardening modulus. And the parameter used in this model is shown in this table. Okay, and then we have choose the material for simulating the frame structure, right? And before we create the element, we should define this material in Opensees. And for the concrete, we use the uni-axial material concrete to create the concrete material. Okay, and the numbers following the command indicate the material tag, the compressive stress, the strain at the compressive stress, and the crushing stress, and the strain at the crushing strain. Okay, and it is noticed that all of these numbers should be negative. Okay, and if you use the positive ones, and the Opensees will transfer all these positive values into negative automatic. Okay, and for the reinforcing bar, we use the uni-axial material steel to define the material. Okay, and the numbers following the command indicates the material tag, the elastic modulus, the yield stress, the isotropic, and the kinematic hardening modulus. Okay. So using all these commands, we can define the material for the frame structure. Okay. And before we create the beam column element, we also should define the section for each column and beam. And normally, we will use the section command to define the section of the beam or column. Okay, and here we use the fiber section to simulate the nonlinearity of the beam and columns. Okay, so we use the TCL command section fiber to create the fiber section for the beam. Okay, and here this one means the tag of the section. Okay. And inside the section fiber, we use the patch cord and the layer straight to simulate the concrete and the steel. For example, for the patch cord, the numbers following the patch cord indicates the material tag and the numbers of fibers in the local Y and Z directions. And the following 8 numbers indicates the coordinates of the 4 point, which creates the area of the core concrete. For example, this one, minus 0.25 and 0.2. It's this point, okay, this point. And minus 0.25 minus 0.2 is this point. And 0.25 minus 0.2 is this point, okay? And 0.25 and 0.2 is this point. So it creates the section for the core concrete, okay? And the following command patch cord creates the area for the cover concrete here. Okay, and then we use the layer straight to define the fiber for the steel. Okay, and the numbers following the command indicate the material tag and the number of the steels in a line. Okay, and this one is the area for each steel. Okay, and the following 4 numbers indicates the start and end coordinates of the line. For example, this point is here, right here, and this point is here. And on this line, we have 3 steel fibers. Okay, so using these commands, we can create the section for the middle column. Okay, I think it is very clear. Okay, and using the similar commands, we can build the section for the side column, and the beams, okay, and the piles here, okay. So when we build the node define the material and the section for the beam and the columns, we can then create the element of the beam and the column. Okay, and here we use the displacement-based beam column element using the element beam column command in Opensees. Okay, and the numbers following this command indicates the tag of the element, the two nodes that connected the element, and here NP indicates the Gauss point, the numbers of the Gauss point used in this element. Okay, and this number indicates the section, the beam or column used, and this one indicates the transformation tag. Okay, previously defined here. Yeah, it's linear and tagged one. Okay, so then we can create the column element, beam element, and the pile element using this command. Okay. And then let's take a look at the soil part. At the soil part, it is noticed that the DOF is 2, which means that for the soil part, each node has only two DOFs, which is the two translations in X and Y direction. Okay, it doesn't have the rotation direction. Okay, so firstly we need to define the node of the soil using the node command here. Okay, and then to simulate the realistic condition, we should fix the base of the soil using the fix command. Okay, for example, fix 1611 indicates that the first and the second DOFs of 16 are fixed. Okay, and this one means fixed, and if the value here is 0, it means that the DOF is free. Okay, so here we fix all the nodes at the base. Fix all the nodes at the base. Okay, so okay, then we should define the material used in the soil part. Okay, we use the multi-layered surface clay material in this model, and I will call it MYS model in the following class. Okay, and MYS model is commonly used to simulate the mechanical behavior of the metal and the soil. And Professor Agama and co-workers developed and implemented the material into Opensees to simulate the nonlinearity of the soil. Okay, so it can be seen that the MYS model has a number of similar yield surface, which is used to simulate the plastic material properties of the soil when it's subjected to the cyclic load. Okay, and we use the ND material multi-layered surface clay to define the MYS model in Opensees. Okay, and the numbers following the command indicates the tag of the material, the dimension, the density, the shear modulus, the bulk modulus, yield stress, and maximum shear strain. And you can see that we have defined 4 different MYS model to simulate the 4 different layers, which is previously talked. Okay, 4 different material for 4 different layers. Okay, and we should also notice that for the foundation, we also use the MYS model as well. And we should notice that for the shear modulus, bulk modulus, yield stress, and maximum shear strain of the foundation, the values are set to be very large because we want the foundation to be elastic during the whole loading process. Okay, so we set all these values to a very large number. Okay. And after we define the material, we should define the element here. Okay, and here we use the card with sensitivity to define the soil element. And it is noticed that we could also use the type part here. And the difference between the plot and plot with sensitivity will be discussed later, okay? And the numbers following the command element card with sensitivity indicates the tag of the element, the four nodes, which is counterclockwise of the element, okay? And here, 0.6 indicates the thickness of the model, okay? And for a 2D model, we should choose if it is a plane stress condition or the plane strain condition, okay? And here, in this model, we choose the plane strain condition, okay? And the numbers following the plane strains indicate the number used in this model and the surface pressure. And here, we should notice that it is density, the element density here. And the last two numbers indicates the body force in the x and y direction. Okay, using this command, we have created the soil element. Okay, and to make sure that the soil part is under the pure shear condition, we should tie the boundary nodes at the same depth together. For example, here, the node 92 should be tied to the node 110, and 73 should be tied to 91 using the equal DOF command here, okay? And equal DOF 355312 means the first the displacement in the first and second DOF of the node 35 remains the same as those of node 53. Okay, and we should also notice that the first line equal DOF 16 34 12 should be deleted here, right? You can write this command in your model. Okay, that is because for the node 16 and 34 we have already used the fixed command to constrain the DOFs. Okay, when you use the fixed and the DOFs here are fixed, it means that the memories of the DOFs in Opensees have already been deleted. Okay, so if they are deleted, then you cannot use the equal DOF command here. Okay. Okay. Now let's talk about the interaction between the soil and the pile. Okay. And also take this part as an example. We have already said that we need to tie the node of the pile to the node of the soil here, 7 and 105. Okay. Also use the equal DOF command. Okay. Equal DOF 7 105 in the x and y directions. Okay. And here it's a it's simplified method to simulate the interaction between the piles and the soil. Okay, then we should define some recorders for the node, for the beam column element and the soil element. Okay. For example, here the first three lines indicates that we have recorded the displacement in the x and y directions of the node 4, 5, 6. Okay, and in the middle we have
recording in progress.
We have recorded the deformation and the force of the specific element here, and we should notice that these two means the second Gauss point of the element. Okay, and then here we have recorded the stress and the strain of the soil element. Okay. And after we build the structure of the frame, the soil, and the interaction between the pile and the soil, we we can perform the static analysis at first, okay? And we have just said we want to apply the gravity load to the SSI system. And here we defined a load pattern tagged 2. And the type of the load is constant, which means that the gravity load is applied on the SSI system all the time, including the static analysis and dynamic analysis, okay? And inside the load pattern, we use the load command to apply the nodal force, okay? And the numbers following the command indicates the tag of the node, the the force in the X, Y, and the rotation directions. Okay, and then we should use these commands to perform the static analysis for this gravity load. Okay, and after the static analysis, we should apply the uniform excitation on the base of the soil. Okay, don't forget to use the Y analysis command to clear the static analysis. Okay, and use all these commands to perform the dynamic analysis. And notice here that we defined a load pattern uniform excitation with tagged 1 and in the X direction, and use the earthquake acceleration, okay? And the time series is included in this file, and the acceleration value is the value in this file magnified by the factor 3. Okay, then we can perform the earthquake acceleration to the whole SSI system using these commands. Okay, and after we do the static and dynamic analysis, we can output the results for the SSI system. Okay, and here the left figure shows the moment curvature responses of the third Gauss point in the seventh beam element. And the figures on the right shows the shear stress responses of the third Gauss point in the 37th soil element. Okay. Okay, now let's have some discussions here, right? Firstly is about the density. If the density of the soil is 2, how can you define the density in the model? Because you should notice that when we define the material, we have here, we have a material density here, right? And also when we define the element quadratic sensitivity, we also have a density here. It's the element density. And how can we define the real soil density here? I think you have my my model in your computer, right? You can try to set the material density to 1, and also set the element density to 1 as well. And you can run the model and to see if the results are the same with this one. Okay, and it is verified that when you use the quad with sensitivity, the soil density is the summary of the material density and the element density. Okay, and let's talk about the difference between the quad and quad sensitivity. And it can be seen that the quad sensitivity is developed based on the element quad, but has the ability to stimulate the sensitivity response to simulate the response sensitivity analysis. Okay, and the model I sent to you has already changed this type. I have changed the quad with sensitivity to quad. Okay, and if you can open if you can run Opensees in your computer, you can try to run this model, and you will find the system, the model cannot be converged. Okay, cannot be converged. This is because when you use the quad element, the real soil density is the element density. Okay, no matter how you change the material density, the material density is not considered in Opensees. Okay, however, when you use quad element and the material density is 0, the program may be something wrong. Okay, and you can change the material density to 1 to 2 to 100 to 1000. It doesn't matter, and the program will give you the right answers, right result. Okay, so this is the difference between the quad and quad with sensitivity. You should be noticed about the density here. Okay, you should be noticed. Okay, the next topic is about in the previous example, we applied the simple pure condition. Okay, and here we are wondering how to simulate the SSI system using the artificial boundary condition. Okay, and here I have built a very small SSI system to show you how to do it. Okay, this is the soil part, and the red line indicates the frame structure and the piles. Okay, and if we want to add the artificial boundary to the SSI system, we should firstly create the nodes at the same precision of the boundary node here. Okay, for example, to create the nodes at the same precision of the boundary nodes and connect these two nodes using the springs and the dampers in the X and Y direction. Okay, and here, for example, the node 10 has the coordinates of 2.40, right? So at the same place, 2.40, we create another node tagged 25, okay? And connect them using the springs, the whiskers in the X and Y directions. And when we do this, when we can simulate the effect of the surrounding soil to the boundary of the SSI system. Okay, to achieve this, we should firstly define what? Define the material of the spring and the dampers. and we use the uniaxial material elastic to define the material for the springs, and we use the uniaxial material viscous to define the material for the dampers. Okay, and also we should use the zero length element, use the to connect these two nodes. Okay, the numbers following the command element zero length indicates the element tag, the two nodes that should be connected, and the material means the four materials used in this element, and the direction indicates the material direction. For example, here 1001, material 1001 has the direction in the X direction. Okay, 1001 is used to simulate the springs. Okay, so it means here this spring used the 1001 material, and here for this damper is used the 1101, right? It is in the Y direction. Okay, so when we use the zero length element, we can connect this node to simulate the artificial boundary of the SSI system. Okay, and we should also notice that when we use the artificial boundary here,
we could not apply the earthquake acceleration to the base of the SSI system directly, but you have to translate the acceleration to the force and apply them to the boundary node, okay? So firstly, we need to define a time series which stores the earthquake acceleration, okay? And then define a load pattern here with tag, here with the 111 tag, okay? And inside the load pattern, we should apply the force on the node of the boundary, okay? And here, we should notice that the exactly force was calculated by the load magnitude and the acceleration stored in the file. Okay, using all these commands, we can add the artificial boundaries to the SSI system. Okay, and I have also sent the model to you. You can try to run the system and see if there are any problems. Okay. Okay, the next topic is about how to simulate the volume of the piles, because when we build the beams, columns, and the piles, the beam column element is just a line, right? It ignores the volume of the of the piles. So so this is the red line indicates the piles, and we could add a set of radial rigid beam column links here to to simulate the volume of the piles. And these rigid beam links are normal to the piles longitudinal axis. Okay, and also we should notice that we should tie the node of the piles, for example, the node B to the node of the soil, for example, D here, using the EQDOF, which have talked in the previous example. Okay. Okay. Now I have strongly recommended you the two books, which is really good for the new learners of Opensees, and the books are both written by Professor Quan Gu in Xiamen University, and the left one is written in Chinese, and it's called the Opensees 实用教程, and the right one is written in English. It's called A Practical Guide to Opensees. And these two books covers a lot of areas. For example, the frame structure, the frame shear wall structure, soil liquefaction, SSI system, fluid solid coupling system, high-speed railway system, and sensitivity analysis, reliability analysis, optimization analysis, and also the meshless method, paradigmatic, and the integration technique between the Opensees and other software. And also, the books have also teach you how to build the Opensees source code and how to add the material, the element in Opensees. Okay, and all of the numerical mentioned in these two books have been uploaded to our official website, github.com/openseesxmu. You can download all the numerical examples and the source code from this website. Okay. And also, I recommended you when you study the Opensees, when you have something not understand, you can search the official website of Opensees Wiki, to try to solve your problems. Okay. Okay, my time is up, and if you have any problems, and feel free to contact me. And thank you so much. And the next, and Professor Qiu Zijian will spend the next hour with you. Okay, thank you.
Hello, hello. Hope I use this one. Either is fine. Okay. Either is fine. Yeah, it's my turn. Hello, everyone. Hello. I'm Q. Qiu Zhijian from Xiamen University. I got my PhD 3 years ago at the University of California, San Diego, under Professor Ahmad Elgama. I have been working on Opensees for more than 12 years. In past 10 years, we have developed several material models and elements into the Opensees. And we also use Opensees to perform a lot of practical applications in California. Yeah, I'm happy to be here to share my knowledge with you. Today I will be introducing geotechnical modeling in Openseas. So here is the outline to our presentation today. I will cover 3 main sections. The first section is geotechnical elements and material models in Openseas. In this section, I will discuss several solid elements and soil constitutive models. So the second section will be geotechnical examples using Openseas that you might be interested in, including embankment, earth dam, and soil structural interaction. The last section is Openseas geotechnical pre and the post processes that develop by our group in past maybe 20 years. So before our presentation, I have a question for you. So how many of you guys are doing geotechnical? You? Okay. Okay. Only 2, 3, 4. Only 4. Only 4 guys. Okay. So I know most of you guys are doing structures. So you guys working on geotechnical. Okay. Okay. Let's get started. So if you search Openseas website, you will find a lot of solid elements. So these elements can be divided into 2 classes, one for dry soil and the other one for saturated soil. So what's the difference? The difference is dry soil is means no water, right? Or drain condition. And the saturated soil means water. So there's an interaction between the solid and the fluid. So for dry soil, we have a lot of solid elements. For example, the cold element for 2D analysis and brick elements for 3D analysis. So here, SSP, we have called UP. We have SSP called UP. So this element is developed recently for analysis because there's only one single integration for each element. So it's similar to SSP brick. For saturated soil, we have UP elements here developed by Professor Ahmad Elgama's group at the UCSD. So it includes 4 nodes called UP, brick UP. So U here represent displacement degree freedom, and P represent the pore pressure degree freedom. So we also have 2D called UP and the 3D brick UP. We also have higher order UP element such as 94 node called UP and 28 node brick UP. So we have so many UP elements. So let me introduce code element briefly. Here is a command. If you look at command, there is several parameters, right? You have to define 4 nodes, defining node element boundary in counterclockwise, such as N1, N2, N3, and N4. You need to specify element thickness, for example, 1 meter or 2 meter. Then the type parameter can be either plane strain or plane stress. So for geotechnical problem, most of them are plane strain, right? Not plane stress. I mean, if you are doing 2D analysis, so plane strain normally for concrete plate or steel plate or shell, right? So in this 2D model, you have to define all the required arguments. For example, the element tag, the material tag. So the parameters in this bracket are optional. Okay, so let's look at the saturated soil. So normally we use cold UP element or brick UP element. Like I said, U represent displacement degree freedom and P represent pore pressure degree freedom. So this is a fully saturated UP element, right? So what's the difference between cold UP element and the UP and cold element? So the difference is it's fully saturated, right? There's water, so you have to define the bulk. You have to define the bulk modulus of the fluid. You know that the water is incompressible material, so the bulk modulus here is pretty high, like 2.2 times 10 to 6 kPa. You have to define the fluid mass density, for example, 1 ton per meters cubic, right? You have to specify permeability coefficient in horizontal and the vertical direction. As I just mentioned, this is a fully coupled UP element. You have soil, you have water, right? So during shaking or during other loading condition, the water will pass through the particles. So you have to specify permeability value. So for gravel or for sand, the particle size is large. That's why the permeability value for gravel or for sand are relatively larger. For example, 10 to minus 3 centimeter here. But for silt or clay, the particle size is very small. So that's why the permeability for those material will be low, so that the water is very hard to pass through the particles. So let's move on to soil constituent models. The first one is pretty simple, linear elastic material model, right? So to characterize the response of soil in its elastic range. So it's pretty simple. You just need to define the elastic modulus and Poisson ratio. Most of our applications, we use elastoplastic material models to characterize the nonlinear stress and strain response of the soil. So if you look at the Opensees website, you will find a lot of soil materials here, including cyclic CP here. Cyclic CP, this is developed by Tsinghua University. And you have Manzari Dafales material from UC Davis. You also have pressure independent material, pressure dependent multi-yield surface material, pressure dependent multi-yield 02 and 03. So those material are developed by our group, Professor Ahmed Elgamas at the UCSD. And you also have PM4 sand and PM4 silt. So those two materials are very popular right now in FLAG. You might know. So stress density material was developed by Professor Kubry Nowicki and Professor Ishihara from Japan. So all these materials work for linear or nonlinear drain or undrained soil response on the general 2D or 3D static or dynamic loading conditions. So so let me briefly introduce pressure independent multi-year model. So this model was developed to simulate monotonic or cyclic response of materials whose shear behavior is insensitive to the confinement change. So this means the shear strength of this material is nothing to do with the confinement change. So this material include, for example, organic soil or clay under fast or undrained loading conditions. So basically, this model is for clay under fast loading. So there's no water, and we don't care about the confinement change. So if you look at this parameter, if you look at the command, the key parameters to this material include reference shear modulus and reference bulk modulus and cohesion. Cohesion is the maximum shear strength and peak shear strength. So peak shear strength is gamma here, corresponds to the maximum shear strength. So if you have shear modulus, you have cohesion and you have peak shear strength, then this backbone curve will be defined. Like I said, this is a multi-year surface. We have a parameter to define the number of yield surface here. So the default value is 20. You don't have to define. If you want more, for example, 40 or 60, then you can just you can just put number here in here. So, but no more than 100, because if there are too many yield surface, the computation will be very expensive. So, like I said, this model is generally used for clay, not for sand. But if you want to specify friction angle, right? I'm not sure you are familiar with the soil mechanics. For soil, we have cohesion and the friction angle. So when we simulate clay, we just use cohesion. But for sand, normally we use cohesion and the friction angle. So for this model, if you want to simulate drain soil, then you can put friction angle here, so that you can see the command here, friction angle, and you need to also define pressure dependent coefficient so that the cohesion and the stiffness will be automatically updated according to this friction angle and the confinement. So this model is widely used for simulating clay. Now let's look at the material properties for this model. We have soft clay here, we have medium clay, and the stiff clay. So for soft clay, the shear modulus is relatively lower. For example, is 13 MPa, and the cohesion is 18 kPa. For stiff clay, the cohesion will be 75 kPa, so it's much larger. Means that this soil is rigid. It's not rigid, but it's stiffer. It's stiffer. So in this table, we don't specify friction angle, right? If you want, then you can put friction angle here. So the figure to the right is an example of the soil response. So it looks perfect, right, on the cyclic loading. So the next model is pressure dependent multi-yield surface 02 model. So this model is widely used by many researchers currently. So it's an elastic material for simulating the essential response characteristic of pressure sensitive soil materials. So pressure independent means pressure insensitive. But for this model, it's pressure sensitive material under general loading condition means the shear strength will be changed due to the confinement change. So, so the characteristics of this model include dilatancy, means shear induced volume change or dilation, and the non-flow liquefaction, we call it cyclic mobility. So what's the meaning of cyclic mobility? So for this model, we focus on non-flow liquefaction, means that the lateral deformation is limited. It cannot deform forever. So like flow liquefaction means landslide, right? So the displacement can diverge forever, maybe 100 meter or 200 meter. But this model, we focus on non-flow liquefaction. So the deformation is limited. So these characteristics typically exhibit in sands or silt during monotonic or cyclic loading. So this is also pressure multi-year surface and defined in principal effective stress. So the figure here show the logic of the model. So for the soil, we have a PD surface line, which means phase transformation. So below this PD surface, we have contraction. The soil compacted. And below this PD surface, we have dilation, means the volume of the soil is increased on the shear loading. So if you look at the mechanism here, below the PD surface, for example, 0 to 1 and 6 to 7 is within the PD surface, means contraction. But above the PD surface is dilation. So when the soil is under cyclic loading, and the confinement will be gradually reduced from 0 to 1 to 3, 4, 5, 6, 7, 9, 10, maybe 11. So when the confinement is low and you keep loading, there is a large deformation, like a 7 to 8. This is a post-liquefaction deformation from 7 to 8. This mechanism is defined in strain space because why do we need to define this logic in strain space? Because you see from 7 to 8, the shear stress did not change, but the strain accumulated a lot. So it's impossible to define this logic in stress space. So that's why we define this in strain space. I'm not showing here. So let's look at the parameters to this model. We have relative density, 30% means loose sand. So this sand is very easy to be liquefied, means very soft, very loose soil. So you can see the contraction parameter here is high, and dilation parameter is low, means this is a contractive behavior of soil for loose sand. I'm not sure you are familiar with this behavior. So with the increase of relative density, for example, 50%, 60%, and 75% here, the soil becomes denser and denser, means that the soil is better and better. It become good soil. So it's not easy to get liquefied. That's why the contraction parameter here is lower, and the dilation parameter here is high. So, which means when the soil becomes denser and denser, it's getting better and better. So it will be harder to get liquefied. Let me show you some of the representative results. So for PDMY02, as I just mentioned, we have dilatancy, like the contraction and dilation. We have cyclic mobility, means the non-flow liquefaction. And we have post-liquefaction shear deformation. So in addition to this key characteristics, we also have fabric change. So fabric change right now is well recognized by researchers because the soil is made of particles, right? And so during shaking or during shearing, the fabric will change. So we include this feature. So for example, you have a soil, then you shear the soil, it will expand, right? In this current loading cycle. In next loading cycle, this soil will become much more contractive. So this is called fabric change. We also have K sigma effect. So K sigma effect means that the effect of initial confinement. If you are familiar with soil mechanics, you will know that when the soil under higher confinement, the soil will become more contractive, will be liquefied easier. So this is called K sigma effect. We also have post-liquefaction shear deformation. If the soil is level, for example, for a level ground during shaking, the deformation will be symmetric, right? You don't have any accumulated deformation. But for a slope, if you shake a slope, the deformation will be accumulated. So this is called K alpha effect or post-liquefaction shear deformation under initial shear stress bias. So we also include this mechanism. So you can see this figure. You can see this figure. We have initial shear stress. For example, maybe 20 kPa. So under this 20 kPa, then you impose the shaking. The deformation will be accumulated in a cycle by cycle pattern in downslope direction. So this mechanism is very important for soil liquefaction. Like I said, this mechanism is defined in strain space. So I also show the strain space here. If you are familiar, if you are interested in this soil model, then you can check some of our publications for this model. So the latest model is pressure-dependent multi-yield 0.3 model. So what's the difference between 0.2 and the 0.3? So the only difference between 0.2 and the 0.3 model is that the contraction rule is updated. Why do we need to update it? Because in practical engineer, people only care about the block count, SPT block count. People just care about number. For example, the soil SPT value in practical engineering is 5. But our soil model has too many parameters, more than 20. So it's impossible for them to use. So engineer just want one number, for example, N160 here, SPT number 5. So SPT number 5 means loose soil. So this soil can be liquefied. When the number is larger, for example, 15, so this is a medium denser. When the number larger than 30, this is a very dense, so it's hard to get liquefied. So in practical engineering, people only care about this one number. They don't really care about contraction. I don't care contraction, dilation, and any other parameter. So finally, PDMY 03 model is updated to capture this number. So this number can be characterized by liquefaction strength curve. So this model is updated to capture the liquefaction strength curve. Also, we include the effect of confinement. So, so nowadays people I'm more willing to use this model because it can capture the practical block count number, right? Okay, so above is Opensees soil model and elements. So next, I will introduce several practical applications using Opensees. So there are a lot of available examples on Opensees Berkeley website, like simulating a centrifuge test, lateral load pile foundation, one-dimensional consolidation, and 2D site response, and deep foundation subject to liquefaction. So in addition to these examples, we also have a website called Soil Quick, developed by Professor Ahmed Elgama at UCSD. So at this website, you will find a lot of examples, maybe 25. So these examples are very simple for pressure-independent material, pressure-dependent material, and solid fully coupled elements for one single element or 3D element or soil column. So let me show you a simple example to 10 meters saturated column inclined by 4 degrees on the sine wave base shaking. So why do we put the inclination 4 degree here? Like I said, the deformation will be accumulated under this initial shear stress. So in this model, you have to define the parameter, for example, shear modulus, bulk modulus. You have to specify like permeability here and vertical permeability. So for this modeling, we use 10 elements with only 1 meter in X direction and Y direction. So this is the soil column, 10 meter depth, 10 elements. Now you are ready to create a model. We use pressure dependent multi-year surface model. This is for saturated soil analysis. Right now you need to define the nodes here according to the coordinates. Then you define elements according to the node number here. As I just mentioned, you need to define bulk modulus, mass density, permeability here. So next, we have to define the boundary condition, right? For this soil column, you have to fix the base, and we fix the pore pressure at the top to specify the water table because it's a saturated analysis. So for left node, we tie all node degree freedom at the same level. Means that this node tied to this node at the same level, so that the column just move horizontally as 1D soil response. So here we perform gravity analysis, and after that we impose input motion here, and we do dynamic analysis here. This example is available at the SoilQuake Opensees here. We also provide MATLAB plotting file here, so you can plot the results. Also on this website, we show the results like shear stress and shear strain at different depths, like 2, 6, and 10 meter. We also show excess pore pressure and acceleration. So the figure here, I just showed the shear stress versus shear strain at the 10 meter depths. So you can see that the deformation is accumulated in downslope direction, right? Because I just mentioned the inclination angle is 4 degrees. So the deformation is accumulated in a cycle by cycle pattern in one direction. So this is very normal in soil saturated soil liquefaction analysis. So this is a very simple example. Now I will show you some of the practical applications using Opensees, just to let you know what we can do in Opensees, right? We don't just do like element tests or soil column. We can do a lot of practical applications using Opensees, right? So the first example is 2D slope ground. So this model was verified by many centrifugal tests in past 5 years. So we create finite element mesh for this mildly sloping ground. The inclination angle is 5 degrees, and all the model is underwater. So for this model, we have to specify the water pressure on the ground surface node. And this figure just show the pore pressure distribution. So it's realistic, right? Because the pore pressure is increasing along the depths. So this figure on the right is deformation contour at the end of shaking. Because there's inclination. So at the end of shaking, the deformation is downward. So the arrow here just show the direction of the deformation. We also show the shear stress and the shear strain in the middle. So you can see that on the shaking and the initial inclination, the accumulation is accumulated cycle by cycle, right? So that's why we need to define this logic in soil model. So this is another example, 2D sheet pile retaining wall. It was also verified by many centrifuge tests called LEAP, liquefaction analysis, experiment analysis project. You will find a lot of centrifuge data there. Also, we create finite element mesh for it. We use elastic spin column to model the sheet pile. The upper layer, the green part here, is liquefiable layer, and the bottom yellow here is a non-liquefiable layer, so that it can hold the pile. So this figure shows the pore pressure distribution. I forgot to mention that we also specify node pressure here and the hydraulic pressure on the pile. So this figure shows the deformation contour at the end of shaking. So we also have sliding connection between the pile and the soil. So at the end of shaking, you can see the soil sliding along the pile. And when the soil is liquefied here, the deformation will be large, and it will push the pile to rotate. So this is a simple example for sheet pile retaining wall. We also conduct a lot of analysis, such as 2D earth stem. So the first one is embankment, and it was also verified by centrifuge test. So the bottom layer here is liquefiable layer. So at the end of shaking, due to the initial shear stress at the slope toy, the deformation will be large here on both sides. So in addition to this small scale model, we also conduct large scale earth stem motivated by actual earth stem. For example, this one, we also created finite element mesh for it. It's plane strain, right? So at the end of shaking, because the log field here is very rigid, so the deformation will be low. But the liquefiable layer here is loose. So when the soil is liquefied, the earth stem will be settled, reaching about like 3.5 meter, will be very high. So this is a 2D model. So for 3D analysis, as you might know, most of the slope failure can be triggered by strain softening behavior. So on this basis, we develop a strain softening model in Opensees. So you can capture the strain softening behavior of like quick clay, sensitive clay, or frozen soil. So so we also create a 3D finite element mesh for a 3D slope. And during shaking, you will see that the soil reach the maximum shear stress and then reach the residual. So which means it's softened. Then a large deformation was developed in the slope. So this just for 3D slope failure. The model is also available on Soil Quick. You might need to check. So we also did 3D shallow foundation settlement. It was also verified by large scale 1G shake table test. There are two towers here. We have a shallow foundation here. The middle layer is liquefiable layer. So during shaking, the middle layer is liquefied. It becomes water. So the tower at the top just settled into the ground about 0.4 meter. So this is foundation settlement. So another large scale computation using Opensees is a 3D multi-span bridge ground system. So this is a actual bridge in California. It's an 18-span bridge. So we also create finite element mesh to this bridge. We use brick UP element, and we use 4-space beam column element with fiber section to model the bridge. But as Professor Wangley just said, the 4 spin column did not have diameter. So we use rigid link. Here we use rigid link here to create a space occupied by the pile. And between the pile and the solid element, we have 3 springs to account for the interaction between the pile and the solid and the soil, including the axial interaction and the skin friction around the pile. So we did a lot of analysis for this bridge. We also compare the damage. So just a suggestion: if you conduct a simulation, you probably need to compare the mechanism with actual scenario, right? So this is the actual bridge failure in New Zealand bridge. Is similar here because in one side there's more liquefiable soil. So on the shaking, the deformation on this side is very large, but on the other side, there is less liquefiable soil. So that's why when the soil is liquefied, the large deformation here push the bridge in one direction and make the bridge to get damaged. So this is the idea. We also conduct 3D short span bridge ground system. I mean, it's similar, right? So you just create finite element mesh, and we just use the spring to account for the interaction between the pile and the soil, and we can analysis. So after the end of shaking, both sides just push the bridge to the middle. So this is quite similar to the bridge failure in New Zealand earthquake. So I'm not showing here. We have published papers. We also analysis 3D arch bridge ground system, since deep foundation can be damaged by lateral spreading. So we don't have to use deep foundation, right? So we can build shallow foundation here as an arch bridge here. So during shaking, although the deformation on both sides is large, there's no damage to foundation. We don't have foundation, but the arch deformation reach about 0.12 meter, and the settlement is a little bit high, like for example 0.2 meter. So we need to care about the settlement to this kind of bridge. I think this is the last example to pile supportive wharf. So it's similar to bridge. It's port structure. We also use force beam column to model the bridge, and we have soil here. After the end of shaking, large deformation here push the bridge to the water side. So it's a port structure. About examples are 3D bridge ground system. So they are complicated. It's very hard for engineer to run or understand or design the bridge, right? So that's why BNWF, this is a nonlinear Winkler foundation model, is developed because it's a simplified method. So the deep foundation is modeled as a column, and the soil is modeled as a PY spring. So right now you don't have to run finite element model. You can just impose the displacement estimate from lateral spreading, and you impose the displacement onto the pile foundation, as you can see here. So here's the pile. You have the spring, then you just impose the displacement profile onto the spring. Then the spring will transfer the force to the pile here. So you can see here, with the increase of displacement profile, the pile deformation will increase. So this is a very simplified method for engineering to design foundation. So for 3D bridge foundation, we can do similar things, right? We can put 3 springs: horizontal PY spring, and the transverse PY spring to represent the soil. So right now we don't have soil brick elements. You can put TZ spring in vertical direction to account for the interaction like settlement or drag force. You can put QZ spring at the base to model the and the bearing, right? So there are several UniX materials available in Opensees, which are PY simple one, TZ simple one, and the QZ simple one. So let's look at the PY simple one. We have material tag, we have soil type. So soil type here, you have one for backbone curve or PY curve for soft clay. So this approximate matlock. So this one is widely used. And if you put two here, so this is a backbone curve of PY for sand, approximate API. So these two springs are widely used in wind turbine, right? And in this UniX material, you also had to specify ultimate capacity or PY and a displacement at which 50% of ultimate strength. So this this model can be also found on Opensees website. Here I just show some of the representative results. PY leak one, PY simple one did not consider liquefaction effect. So that's why PY leak one was developed to account for liquefaction analysis by Professor Ross Bollinger at UC Davis. So this model is very powerful because the PY spring will call the excess pore pressure or effective stress from surrounding soil, and in the code it will compute the force and impose on the pile. So for level ground, like I said, the deformation is symmetric, right? So for slope or for infinite slope, or under initial shear stress, there is a lateral spreading. So the soil will push the pile in one direction, cycle by cycle here. So this one, the difference between liquid one and the simple one is that this PY liquid one include liquefaction effect. So right now, you don't have to model full 3D finite element model of bridge ground system. So you can do a simplified method, right? You just model the bridge itself, and then you put soil column here, and you put PY leak in between the foundation and the soil column, so that the PY curve will call the pore pressure from the soil column and impose the pile. So this model is much simpler compared to finite element model. So right now the question is, we have 3D finite element model. Why do we need this kind of simplified method? Because finite elements 3D bridge ground system is computationally expensive. Nowadays, people more care about the performance-based earthquake engineering design, right? So we need maybe 1,000 run or 10,000 run in a day. So it's impossible for 3D finite element model. So that's why people develop efficient. So we call this efficient bridge model, so that you can finish the run in a couple of minutes, and you get like 10,000 or 100,000 runs a day. So you can get the results immediately, and you do performance-based earthquake engineering design, right? So about several practical applications. So last section, I will discuss several geotechnical pre and post processes developed by our group, include Opensees PO. The Opensees PO here, just models 3D pipe ground interaction. We have MS bridge to analyze multi-span bridge system. We also have cyclic 1D to conduct 1D site response analysis. We also have mesh-free framework developed recently by me, and we have strength softening model here. we have Opensees geotechnical capabilities here. We show some examples here. We have some downhole array here, some data. We have legacy software. So this is a very old software, including like Shadow Foundation or Earth Dam. So this website was developed by Professor Ahmad Elgaman at the UCSD. So right now, this website was maintained. It is maintained by me. So if you have any questions, you just contact me. So let me go over the software quickly. So the first one is Cyclic 1D. So Cyclic 1D is PC-based graphical pre and post user interface for site response analysis for liquefaction-induced lattice deformation, immediately inclined infinite slope. So on this website, you can just download this Cyclic 1D and install Cyclic 1D. So this is a very simple software. So here is the interface to this Cyclic 1D. You can conduct elastic analysis of plastic analysis. You can specify the soil profile. So the soil profile is the same as this one. It's the same as this one. So you can specify the total height of the model. You can specify number of elements. You can specify water table at which depths. You can specify inclination angle. Like I said, it will introduce more deformation. You can specify the boundary condition at the base, like rigid or like transmitting boundary or flexible boundary. You can specify input motion here. You can specify radial damping. You can specify soil property to each layer. Then you just save the model and run, you get the results. So it's pretty simple and straightforward software. So the next one is Opensees PO. So this one is very powerful. It can model pile and the ground interaction. So in this model, you step one, you can specify property to each layer. For example, I want 3 layer. Then you put 1, 2, 3 layer here and you specify property to each layer. You can do saturated soil here, right? If you uncheck here, then it's dry. If you check here, it's saturated soil, then you specify water table. So it's very user-friendly. The next step, you can define the pile. For example, you define the pile type, for example, circular or rectangular. You specify a diameter, the total length, and the mass density, and the pile head connection, and the lump mass at the top, because for this software, we don't have superstructure. So if you want superstructure, it's a lump mass. You put the mass at top. So similarly, for this pile, you can specify beam column element type. For example, force space beam column or displacement based beam column. You can couple with fiber section or linear fiber section. That's fine. So these are additional applications using Opensees PO. So just show what you can do in Opensees PO. For example, you can do one single pile in the middle. You can do pile group in the ground. You can do large container embedded in soil, right? So for example, nuclear power station is embedded structure, is rigid. So you can model that using this software. You can do like stone column mitigation here. So this is for ground improvement. You just replace the material property by high permeability and the stone stone material, and we can do 3D site response. So we use this software to run a lot of analysis. So here is an example. This 1G shake table test conducted at the UCSD. We use this Opensees PO to match the shake table test. So during shaking, the soil pushed the pile in downslope direction and the pile deformed. So this Opensees PO was verified by many experiments. So the last software is MS Bridge. So MS Bridge is also very powerful. It's a PC graphical pre and post processes in 3D multi-span bridge response. So it's also available online. It's also available on SoilQuick. Um, so um, so what you can do in this software? You can do pushover analysis. You can do model shape analysis. You can do time history. You can do equivalent static analysis, and you can do PBE analysis, performance-based earthquake engineering analysis. So in this software, you can do straight bridge. You can do curve bridge. You can do without any foundation, and you can do with foundation. So the color here is a foundation. So for this MS bridge, we don't have solid element. We just use PY spring to represent the soil. So in this software, it's pretty straightforward. So step one, you define the model and check the response. Spans here, you can define how many spans you want. For example, we have 1, 2, 3, 4. We have 4 spans. You can specify whatever you want. And deck, you specify the cross section of the deck. You specify the band cap, the column, foundation, and the abutment bridge, and mesh. You can refine the mesh here. So you can do quick check of the model response. For example, you can view the natural frequency of the bridge, and you can view gravity analysis for longitudinal or for transverse response. So this is step one. Like I said, this is very simple software. We don't have solid element here. So you just need to define the PY spring to represent the soil. For example, here, when you define the foundation spring, you can choose, for example, sand wreath here, and you specify the pile width here. For example, is 60 inch, maybe 1.2 meter, maybe 1.5 meter, and you specify submerged unit weight here. You specify friction angle, for example, 30 degree. Then this software will calculate the PY curve automatically according to the depth. So normally, with the increase of depth, the spring will be stronger, right? Because as the depth, the spring will be stronger. So in this software, we can also do PBE analysis. Like I said, PBE, performance-based earthquake engineering, is becoming more and more popular because it will avoid the uncertainty in modeling, right? If you just run one single motion, there are many uncertainties related to like the material property, like the motion characteristics, and many other parameters. So that's why people do performance-based earthquake engineering right now. So in this MS bridge, we provide a lot of input motions here. You can select them and just run. We also put scale factor here for longitudinal, transverse, and vertical. So we can also do incremental dynamic analysis to run the performance-based analysis. For example, seismic fragility or seismic resilience. So in this software, we also show we also display intensity measures for this earthquake. For example, the PGA, PGV, PGD, and many other intensity measures distribution. Finally, yeah, we have a couple minutes left. So the last part is uses this soil model for seismic response in other software. So for geotechnique, guys, you probably use FLAC or use LSTANA or any other software. We also provide the link, the DLL link, so that you can connect our soil model to the software, for example, FLAC or LSTANA, to run the model using our soil model. We also provide example. For example, we also provide example here, like 10-meter saturated median soil column subject to base shaking in FLAC and LSTANA. respectively. So you can check them if you are interested in. So above is my presentation. Thank you for listening. If you have any more questions, I would be more than happy to answer. Yeah, just send me email. Yeah, thank you.
I think so. Okay, so small presentation. My name is Massimo Petracca from Italy, and I'm from Asda Software. We are a private company in Italy, and we developed the user interface for STKO, for Opensees STKO, which is a pre and post processor. But we also do contribute to the Opensees source code community. So today, I will first do in this first hour and a half, we will try to implement a new constitutive model in Opensees. So I will show you how to compile Opensees and how to add a new component in Opensees. And for this, you need to do some compilation, or at least if you are interested in, and if you want to do it now. And in the next hour, so from 4:30 to 5:30, we are going to do an application example. It will be a shear wall modeled with shells, and we are going to do a static cyclic analysis. We will do it in STKO, and I will show you how you can use it. Is it fine? Okay. So just before we start, how many of you have some experience in compiling source code in C++? No one. Okay. So it will take a little bit. I hope you will find it interesting. Oh, someone. Okay, there is someone online. Okay, the problem with compiling the source code with respect to writing Python code or MATLAB or any other interpreted languages is the concept of compilation. So you have to compile something. It's not just about writing the code and run it, okay? So for this reason, yesterday I sent you the first part of the presentation at the beginning, then the full presentation. In the first part of the presentation, you have the installation, how to install all the prerequisites that you need to run the compilation. I don't know if some of you already did it because it's going to take a little bit of time. Is there someone that did it? Okay. So I will try to explain it slowly. You can try to do it now, and then probably in the last half an hour of this lesson, I will help anyone that is trying to compile, okay? Because it's going to take too much time now to do the download and everything. So on the first slide, you have the first link. So how can you build OpenSea source code? All the information is given in at this link, okay? So if I try to go here, you will see that there is a session called Building Application, and it gives you instruction for both Windows, Linux, and I think also Mac, if you scroll down. Now, what's the problem is that in many cases, if you follow this instruction, they will work, but there are cases in which you may find troubles. For example, the first problem is related to the compilers from Microsoft. They say, for example, the libraries from the Intel that we are going to use are not compatible with the latest compilers from Microsoft. So you should install version 2019. We will see that now this one is not available anymore for free. So we are forced to use this one, and we can solve the problem. You can do something. I put everything into the description, okay? But anyway, the concept, all the steps that you have to follow are summarized here. So I'm going to follow them, okay? So in the first slide, you have the main access point for the building application. Now, before you do all the buildings, especially if you never did it, you need to install all the packages that are required for compiling the code, and also all the other code that you need. Let me see. I cannot find the slides and other material of this lecture. Where can we download it? People online have the link to the drive. People online have a link to access the material. They saying that they don't have it. On the link that I had. We will check it. So at least we will upload it soon if you cannot find it, because we uploaded it yesterday. Just a second. I uploaded it yesterday through the link that you provided. I uploaded two folders called Course Applicative Example Shear Wall STKO and Course Develop Opensees. I don't know if they appeared there. I uploaded. Yeah, sure. Okay, sure. Okay, we are uploading them now. So 1 and 2. Okay. Okay, they will be uploaded soon. I uploaded through the link, the Chingwa link, but probably didn't work. I don't know.
Well, I think it's another link.
Ah,
It's a different link.
It's a different one. Okay. Perfect. So they are going to upload it soon. Okay. Anyway, you will find two folders. The one is for this first session, so code development. And here you will find the presentation. And in the first 10 slides, there are all the instructions of the things that you need to download and install. And then you have few other support material that we will explore later on. And in a second folder, course application example shear wall STKO, there is the example that we are going to do later on with STKO. Oh, just another note. So all of you should have a flyer in your bag with a coupon to have a free license for 1 year of STKO. Okay, so you can download STKO, you can activate the trial license. It will last 30 days. And in the meantime, you can follow the information to extend the license. Okay. Okay, so as I said, the first step is to install all the prerequisites. Okay, so the first one is the Python version. As we have seen yesterday, in many cases, Opensees has some problems with Python version higher than 3.10. So I would suggest you to install Python 3.10. In my case, I installed 3.10.6, but it's not important. The third part here of the version number is not important. Try to install Python 3.10. You just need to Google. Nothing but that. Python 3.10.6 or whatever it is. And hopefully will send me through to the link. Well, anyway, so we don't waste time here. You just Google that and you can install Python 3.6, okay? So the next step is CMake. I will show each one of them. Then we need to download the source code of Opensees in a, let's say, in a developer way, because you can download the source code manually as a zip file. Someone else in the chat. Okay, so you just received in the chat the two folders. Okay, thank you. So after CMake, which is a tool necessary for compiling, you will need to download Git and optionally GitHub Desktop. The first one is necessary, the second one is optional. But if you're not experienced with command lines, probably the second one will be helpful. Let's say it's a visual way of doing the same stuff. And finally, the two, that's why I put them in bold, the two things that takes most of the time, okay? Which is the Visual Studio Community Edition, which is the free edition. Visual Studio is an IDE, so an integrated development environment. Let's say a user interface to the compiler, okay? You can download the 2022, which is the latest one. And as I said before, the default compilers that will be shipped with this version, they will not work with Intel. But I will tell you in the instruction how to install the compilers from the 2019. And finally, after the Visual Studio, once this one is installed, you can download and install Opensees One API. It is important that you first install Visual Studio and then the Intel One API, because when Intel One API is installed, it does some checks on the system and tries to find what Visual Studio version is installed. Okay. Okay. So the next step is Python. Okay. So the first thing, this is, you have to follow this step only if you don't have Python, but I think most of you have Python anyway. Okay. So for those who don't have Python, you can download it. Okay. So here I put the link. You can follow the instruction. When you follow this link, you have several things to download here, but you can see that I highlighted the Windows version 64-bit, which is the executable, not the source code or anything else. Okay, so you download this one, you run the installer, and this is optional, but I prefer, because by default, Python will be installed in C user, your username, app data, so it's a long path. I prefer to have it in a shorter path, so it's easier if you have to navigate through there. So for example, I installed it in C Python 3.10. This one instead is not optional. You have to do it because once you have a fresh installation of Python, you just have the basic built-in packages, but you may need more packages, okay? And you will need for sure NumPy, SciPy, and Matplotlib for some of the examples that we will do. You will need Opensees Spy, and then I will show you how to compile another version of Opensees Spy. But at the beginning, you need it. And then for compilation, you need this package, which is called Conan. And you need an extract version of Conan. You need 1.59.0, which is required for compiling Opensees. And when you want to install something through pip, you can just put the double equal sign. And so you're forcing pip to download that exact version, not the latest one. Okay. So you can just go to the command line, okay, and type these commands. Okay, once Python is installed, pip install NumPy, pip install SciPy, or you can put all of them in a single line and it will do everything together. Okay, something like this: pip install NumPy. Well, in my case, I already have it. Okay, so it's okay, it's already installed. You do the same for everything. Okay. So this one is the first step. It should take a few minutes, so you can do it also now. This is not a problem. The lengthy part will come later on. Next step is CMake. Also here I put a link. You can go here and you have a pretty visible green button to download the executable, and you can just install it. You can install the latest version. There is no problem here. We install it and you download it and you install it. There is nothing special to do here. Now, the next couple of tools that we need is for downloading, contributing to the source code. So of course, there is also a way to download the source code blindly, just downloading the entire zip file. But in this way, it's not easy to see what are the changes that you're doing. It's not easy to navigate through different branches. So if you use this tool, it will be slightly easier for you, slightly easier. And I do recommend it to do it like this because I already created in my repository 2 different branches that have the material already there, the one that I want you to implement now. And I made 2 different branches, one with a starting point from the material. So I set up the files, but I left that empty with some instruction. And the other one is the complete one. So you can see the differences between them. And I will guide you through that later on. So with the first one, you can download Git and then GitHub Desktop, okay? Let me see if I can go through these links. Okay, GIT is here. You can just go to the download for Windows. The latest version is fine. You download it and you install it. And the next one will be GitHub Desktop, okay? Download for Windows 64. There is nothing special here. Okay, I will go slightly fast, and then if you have troubles doing all this stuff, I think we will have half an hour from 4 to 4:30. Now, the real problem is here is Visual Studio. It will take a little bit to download and compile it, and you have to carefully follow some steps, okay? Now, the point is that we are going to install the so-called Community Edition, which is the free one. For the free one, you need to have a Microsoft account to download it. Okay, so you go to this link. But the problem with Microsoft is that they always try to push you in downloading the latest version, which makes sense. But in this particular case, the latest version will give you troubles, okay? So the one thing that you have to do is that you download this one, okay? And once you download it, it's called, I think, Visual Studio Installer. Let me see what's the name of the download. Visual Studio Setup, okay? It's an online installer. So you download a small setup and then it will download things online. So once you have it and you run it, here you have to pay attention, because if you miss this step, you may need to modify the installation later on, okay? So the first time you install Visual Studio, since I told you Visual Studio is a user interface for compiling things, it's not the compiler itself. It asks you, what do you want to develop? For example, in our case, we want to develop C++. And by default, C++ is not selected, okay? So the first thing you have to do is to go into the first tab called Payloads. I'm sorry for the slide is in Italian, but I put a translation here. The first tab is Payloads, which is a block of tools necessary to perform the different operations. For example, if you are a .NET developer, you have tools for .NET. If you do Java, all the other stuff. But in our case, we want to develop C++ desktop applications, okay? So you put a check here, and they will automatically choose some default components, okay? And as you can see here, the default compiler, which is this one, the one that I highlighted, is called MSVC, which stands for Microsoft Visual C++, version 143. This one is the compiler for Visual Studio 2022, which is the latest one, and is the one that is going to give us troubles with Intel, okay? So this is not the only step that you have to do. Before going further, you need to look at the next slide. If you scroll down on the right list of things, you will find that is not selected by default, but you can select the compiler that was coming from Visual Studio 2019, okay? So you select it, and you should be ready to go at this point, okay? So you select this one, and the Windows SDK for Windows 10 or Windows 11 depends on, but the Windows 10 is fine. Once you have this one, you can go on with the installation, because now you have one Visual Studio, which is one interface, but you have two compilers. The latest one, and which is version 143, and the old one, which is the one that we need for Opensees, which is toolset or version 142, okay? Oh, and there is another thing that you shouldn't do, because I tried also this and it wasn't working for me. When I said, okay, I have the compilers for Visual Studio 2019, I may uncheck the latest compilers. It doesn't work, because if you uncheck the default, which are the latest compilers, the Intel One API will have trouble identifying Visual Studio. So don't do anything, do exactly what I told you. So the default payload plus the Visual Studio 2019 compilers, and it should be fine. So you run the installation, it will download, I think, 6 GB of stuff. So it will take a little bit. You can try to run it now for those of you who want to develop some stuff. And yeah, I will help you later on if there are troubles. So once you are done with Visual Studio, you can download the Intel One API, and of course, you can download it before, okay? But what I mean is that the installation of the Intel One API should be done after the installation of Visual Studio. And for the Intel One API, there are two things that you need to download: the base toolkit and the HPC toolkit. Actually, today, you just need the base toolkit, because you're not going to do the compilation of the parallel versions of Opensees. But since you are here, download both of them, because once you compile the Opensees, the parallel version is not too complicated to compile. Okay, so you can download both. When you go to the website, I think I forgot to put a link to the website, but it's not a problem. You just Google for Intel One API. Let me Google here. It's taking a little bit. The VPN. Okay, let me see if I have. No, I disinstalled it. I uninstalled it. Let me see if I can connect with my. Well, anyway, I cannot do it now because I don't have a VPN now. I should set up it, but you can just Google for Intel One API. Can you verify that you will find the link there?
Yep.
Is that one? Okay, perfect. So you go on the download page and you have the buttons for. Oh, but by the way, no, I didn't put the link actually because it's here. When you follow this installation, so if I go to this link here, in the installation, the two links are already provided, okay? So once they tell you, okay, now download Visual Studio, they didn't mention how to solve the problem with Visual Studio 2022, so you can do it as I told you. And then here you have the links for the base toolkit and the HPC toolkit, okay? So you just click here and it goes. Well, probably only Google is. Oh no, probably also here is not going good. Okay. So you get the links from there, okay? Once you have the link, you are going to the download tab, and you will choose the Windows operating system if you're on Windows, and the online installer, offline installer is the same thing, okay? Because anyway, you need to be connected here. So online installer, you do the same. Oh, and by the way, it says that you have to register, but it is not necessary because there is a small button on the bottom, continue as a guest. So it's not strictly necessary to register. And at the end, you will have these two executables, one for the base toolkit and one for the HPC toolkit. You first run the first one and then the second one, okay? In both of them, once you are in the installation is pretty similar for both of them. You just accept the license agreement and you go on with the recommended installation. There is nothing to do, okay? And you do it for both of them, for the base toolkit and after for the HPC. The base toolkit, it will take a little bit more because it's about 16 gigabytes of data, while the HPC is much smaller. So also this one will take about 15 minutes to install, depending on the download speed. Now, I think it will take a little bit of time for you to do all this stuff. I will go on, and if someone of you is trying to download it, then I will help you later on, okay? So once you're done with Visual Studio and the Intel One API, you have all the things necessary for compiling, okay? So the first thing that you have to do is to prepare the building environment. So what I did in my case was to go under C, and I created a folder called desktop, okay? Now it's my case, it's already full, but in your case, it will be slightly empty. You just need a folder called desktop, and here we will create a folder for Opensees, but we will do it later on. The first folder will contain the source code for Opensees and also the compiled Opensees executable for the Opensees TCL and the Opensees Py DLL for the Python version. Here in my case, you see also these two folders, but you will not need them because one is to contain the MAMP solver for parallel computing. We don't have time to do it today. And the other one is something that I use to store all the installed files because I typically compile all the Opensees. So I like to keep them into a deploy folder, but it's not necessary in your case, okay? So you're going to have only these two folders. The first one is for the Opensees source code, and the second one is for a Python virtual environment. We have a question. Should we download the latest base toolkit? Yes, download the latest one. Okay, so as I told you, the Opensees folder is for Opensees, and then we may need a Python virtual environment. So I don't know how many of you knows about the Python virtual environment. Okay, so you know, when you have Python, you have a certain Python version, you install there different packages, okay? And they will be used with that Python version. Now let's assume you want to use the same package but a different version. Like in our case, we want to use the Opensees Py, the official one, but we also want to develop our own Opensees because we are going to put a new material model in there. So we cannot install two different Opensees pies into the same Python. Okay, so what you can do is to create a virtual environment, which is, let's say, a small copy of the current Python environment in which you can install different different packages, and you can switch from one environment to the other depending on your needs. Okay, so I will show you also how to do that. Okay, so the first thing that you need to do is to just create a folder called cdevelop. Okay, and here we will do the everything. Okay, now how to set up the Intel One API libraries. If we come back to the Opensees instructions, let me go here. If we go back to the Opensees instructions, once you set up everything, they give you a set of command lines to run. Now, the mumps one is not necessary, as I told you now, because we don't need to compile the parallel version of Opensees. This one is a special solver for the parallel Opensees version, when you have to run huge models. Not necessary in our case, but we need to follow these other steps, okay? For just actually setting up everything, downloading Opensees, downloading the dependencies, I will go through it later on, setting up the compilation, compiling Opensees and Opensees Spy. We are not going to do these two stuffs because as it is written here, it will not work. So it's a different story. If someone is interested in this, you can contact me or you can write on our user forum and we will guide you through that, but we don't have time now. Okay, there is another session. Can anyone share the link for the recordings of today's section? Is someone recording? I think yes. The recording of today's lesson. Okay. Okay, yeah, they will communicate the link to you. Okay, so the first thing that you see in these comments, don't worry about them, I will explain you what they mean, is this one. So you open a command line and you type this thing here. Now what it is, it's what I've written in slide 13. This one is to set up the Intel One API libraries. So the Intel One API libraries need to set up some environmental variable to work, okay? So if you try to run the command without doing this stuff, it will not work, okay? So the first thing that you have to do is to either type this, so I can just copy this one. You open a standard command line in Windows, and you type like C, program files, x87, Intel One API, set bars. The reason why I have the double quotes is because in program files there is a space, okay? And then you set up the settings, Intel 64 mod, okay? So if you do this, you will see something that gets printed into the command line. This is just a way for the Intel One API to find the different stuff. On Opensees, they tell you to do this because it's the command line way. There is an easier way for me. If you are on Windows and you search here, you just type One API, and you will see that there is the Intel One API command line for Intel 64 for Visual Studio. If you type this one, it's exactly the same thing. So it opens a command line and it runs the setting, okay? So it's much easier. So instead of every time opening the command line and typing that line, you can just open the Intel One API command line, okay? Now, if we have the folder called cdevelop, we can directly go inside that folder like cd, which is change directory, cdevelop. Okay, so we are now inside the develop folder. I think there was a question. Okay. Okay, at this point, we entered inside our develop folder, okay? Now, the next thing is to get Opensees. Now, there are different ways for getting Opensees. If we go to the Opensees documentation, actually on the Opensees GitHub, let me see if I can go there. Not here. Well, if you can Google through Opensees GitHub, you will directly go at this link here. Now I don't have a VPN. And there is a green button on the top where you can, there is an option like download zip file. In that case, it will download the entire source code as a zip file, okay? That is fine. You can unzip it and place it wherever you want, in this case, in the desktop folder. But it's not the optimal way, because in that, yesterday I shared just the first 12 slides because they were just the slides required for the installation, okay? Now they are the full settings and they have been shared here. There is a link up here, okay? If you open this one, you will have the full presentation, okay? Yesterday, I only shared the first part, which was necessary for downloading. That's why I decided to do it before. Okay, so you can either download Opensees manually, or you can get it through Git. If you get it through Git, you are somehow linked to their repository. So you can start using the Git stuff to contribute, to see the differences. If you do it through Git, though, you need to understand the Git commands, and we don't have time now to explain how Git works. So those of you who are already familiar with Git, through the command line, they can do it. Otherwise, you can use the GitHub desktop, which is, let's say, a user-friendly user interface for that. Now, with this command here, you're going to clone the official Opensees repository. The link, it's up here. It's up here in the chat. I think you can just download it. Can you see it? It's not shared, sorry. But if you go on the chat, it's here. Can you reshare it, please? So anyway, if you scroll up into the chat, you will find it. Okay, so here you download the official Opensees repository. Now, in this example, I suggest you to download instead my own fork, which is where I contribute to Opensees, because we are going to do an example on my branch, and my branches now are not in Opensees because we are working on it now, okay? After the Opensees course, I actually will do a pull request, so the new material that we develop now, it will be on the official repository, okay? But for the needs that we have now to compile it, I keep it local to my repository, okay? So you can clone this one. Now, if you don't want to use the Git command line, you can use the GitHub desktop. This is much easier. So you go to my GitHub page. So if you go on GitHub, and now I have this problem with, let me see if I go here. Otherwise, I need a VPN, but it will not allow me to do that. Okay, I have it. So if you go to Opensees, this is my public repository. Actually, okay, this is my, you see here, it's Opensees, but from another guest. It's not from the official Opensees organization. Here you have different branches. We are going to work in these two branches. Cohesive models is a branch where I placed the initial file, which is empty. It's just a file without any source code in there. And this one is the complete one. So it's the one that we are going to build during this simulation, okay? Let me go back to the code. What I wanted to tell you is that if you go to this link, you can either download it manually, as I said before, download zip, but in this way, you don't have the opportunity to go from one branch to another. You cannot see the differences that you are doing in the source code. So I suggest you to use Open with GitHub Desktop. If you install GitHub Desktop and you click this one, it will guide you through the cloning of the repository inside a folder, and you can pick cdevelop, okay? If you do that, the GitHub Desktop will automatically create a folder called Opensees inside cdevelop, okay? So you will have a folder like this with all the source code for Opensees, and this small hidden folder, which is something that Git uses to keep track of changes and everything, okay? Now, the nice thing about this one is that then you have this application, GitHub Desktop, where you have here your repositories. In your case, you will see Opensees, okay? And here you have the different branches. Now, you don't have to worry about this one because you will learn, if you want to, how a repository works. You just need, what you need to know now is that you can go from one branch to another. So we will start here, just to give you an example. Once you download this one, if you go here on cohesive models, the original one, cohesive models, okay, now it is changing from a source code to another, and you will see some stuff that I did. Okay, so this is the nice thing about the software. It shows you the history of all the changes that you did in the source code. So from the moment I copied this folder, I did this first modifications here. Okay, I will go through it later on. Okay, but the thing is that in this branch, I set up all the necessary changes, small changes, to let you have an empty file for the new material model. This empty file will do no calculation anyway, because if you look at the source code of it, okay, I just put the minimum necessary code, because in 1 hour it's impossible to teach you all exactly from zero how to create a new material. But I put instructions. So for example, here you have to do the parsing of the input parameters. And I tell you, and I give a suggestion on how to do it. Okay, so also here, I just put a bunch of placeholders, okay, like this one. So if you try to compile this one, it will not work because the code is not complete everywhere. Okay, so the constructor is empty, the destructor is empty. Here, do your own computation here, which is the main method where we will get a stress from a strain. Okay, so as you can see, it's just an empty file, a template file where we are going to put our code. Okay. On top of that, of course, I made some mistakes, so I fixed them. Okay. And after that, I will start with this one and I will put the source code in there. But at the end, we will end up having this one. Now I made a backup of the new one. On the new one, you can see that what I've done is all these things. For example, I completed the piece of file where I said, okay, this is the instruction, and I actually implemented it, okay? And we will go through it step by step. But what I want to show you now is that with these tools, it's easy to track all the changes that you did. Okay, so that's why you need, or I suggest you to use Git or GitHub Desktop. So back to the presentation. So at this point, you have our own version of Opensees for doing the exercise today. Okay, so here I already told you how the two branches work. Now, there is only one thing that you have to do now that can create problems with the compilation of Opensees Pi, is that once you download Opensees for the first time, just for the very first time, you will find something inside this folder. It's written here. So, what is the folder? Other, Eigen API, Eigen directory. So if you go here, under Other is where Opensees keeps the code of third-party libraries. There is a library that is being used for a plastic material that I'm not going to talk about now, which has a folder called Eigen. This one should be empty. Now, when you download it for the first time, and I'm not going to tell you why, it is not empty. Okay, it's a mess, so it's difficult to explain now. Just delete everything you have inside there. Okay. So once you have this one, you're done with Opensees, or at least you're done with setting up the prerequisite for Opensees. We are going to compile it after we are the new material. Okay. But we can do something before. So as I told you before, we are going to compile Opensees, the opensees.exe, which is the executable for Opensees TCL. But we are also going to compile Opensees Pi for those of you, because I've seen that the majority of you is using Python. So we will also compile Opensees Pi. And since we want to test it, I cannot tell you to replace the official Opensees, because everything you need to do with Opensees, you do it with the official one. So I will tell you how to use the virtual environment in Python. So how does it work? Well, the first thing is that you can decide a name for your virtual environment. In this example, I called it my Pi. in my case, I already have it here in develop MyPy, and it's already full, okay? Now I will show you exactly how this is done, but on another folder. So the first thing that you do is to create a command line. You can use also this one, and you navigate through desktop, cdevelop. And if I'm not wrong, we are already inside cdevelop. So the first thing that I will do is to create a folder for my Python, okay? So mkdir, which is make directory, MyPy. Now in my case, I put another character there just to not overlap with the existing one that I have. Okay, so in this way, you just created a folder, okay? Now with this command here, you are telling Python to create a virtual environment into this folder, okay? Now in my case, I will replace this one with MyPy2, okay? So Python /m -m venv MyPy2. Now it will take a little bit, just a few seconds. Hopefully, because I think it's okay. It's downloading everything, so I had no problem with the VPN. Fantastic. So now inside here, you have a basic installation of Python, which is a virtual environment of your original Python. And here, as you can see, you have a copy of the lib library with the site packages. But inside here, you have just the necessary tools. You don't have all the things that you already installed in your official Python. Like you don't have Opensees Py, you don't have NumPy and everything. Okay. So let's try to install all of them also inside this virtual environment, okay? But to this point, we just created the virtual environment. We need to activate it. As you can see here, I'm not yet inside the virtual environment. I'm inside the official Python. Let me see if there is a question. No, it's because you typed Python /m opspy. You don't have to do it, but anyway, it's saying that it doesn't find Python. So you don't have Python. You have to install Python before, okay? So first of all, there is a mistake here because if you type Python, just Python like this, if you type Python and it doesn't say anything, it means that either you don't have Python or the operating system cannot find Python, okay? If you're sure that you have Python, you may want to check into the environment variables. And inside the path here, well, I cannot modify it now, but okay, here. You have to make sure that you have the path where you have the python.exe, okay? Otherwise, your operating system cannot find it. But this is pretty standard. So if you have Python inside some other installation and you only use it through Anaconda or other stuff, try to type like C, the entire path. Like in my case, is in C Python. C Python. Oh no, I have to exit from here because I'm already in Python. The other option is to type the full path. So I'm in C Python 3.10 python.exe, and you're again inside Python. Okay. But this is up to you. So make sure you have Python and Python is visible to your operating system. And then you don't have to write Python /m opspy, but it's Python -m venv. Okay. Okay. So it's this one, the command, Python, venv, and MyPython2. So as I told you, this first command is just to create the virtual environment, but to use this new Python and not the old one, you need to activate the virtual environment. And you can use this other command here. I will show you now. So you go in where there is the installation folder of a new Python. So it's C, develop, MyPy, in my case is MyPy2, scripts, and activate.path, okay? You run it, and now you can see that it's slightly changed. Now, instead of writing here cdevelop, I have between parentheses MyPy2. Now, in this case, it means that I'm using my new Python. In fact, if I enter here Okay, similar, the same version to the other Python that I have. But if I import NumPy, for example, it will say that I don't have it. Okay, there is no module named NumPy, even though I have it on my own Python. Okay, so you can simply exit and you install all the necessary packages that you need. Okay, so pip install all this stuff. Okay, when you're done with it, you can exit from this Python, which is like C develop mypy, in my case it's mypy2 deactivate scripts, sorry, deactivate.bat. And now you're back to your default Python, okay? Okay, CLS, so I clean everything. You can follow these instructions if you don't want to override your official Python, your official Opensees Py. Okay, so once you're done with it, and I already did it, so now I can safely delete mypy2 because I already did everything inside mypy. And you can see that inside lib, side packages, I have all the things that I installed and also Opensees Py, okay? Okay, so the next thing is to start compiling Opensees. So the first thing that we do when we compile Opensees is to create some folders called build. I already did it, but since now you are inside develop, you can go inside Opensees. So cd Opensees. Now you're inside Opensees, and here you want to create some folders. A first folder called build. I already did it, but you can follow this instruction. You will have a folder called build, which is where we are going to build everything. And here I created 3 folders: sequential, NP, and SP. Sequential is for the single core versions of Opensees, and those are the ones that we are going to compile now. And the others are for the parallel version, so you can skip them because we are not going to do it, okay? And then CD sequential. So when you do CD sequential, you are inside here, okay? CD sequential. CD build, CD sequential. Okay, now we are inside the folder where we are going to compile everything. Now, in your case, this folder will be empty, okay? Now, following the instruction, okay, now just before starting the coding, I want to show you what we are going to do, okay? So I want to explain you the material that we are going to implement. Now, we still have half an hour. No, we still have 1 hour, or no, half an hour now. We are going to create a material that we are going to be using in the next hour for the applicative example. We are going to model a shear wall. Now, when we model shear walls, there are different ways of modeling the reinforcement. The one is to use smeared rebars, which means rebars are modeled as equivalent smeared layers. And this necessarily assumes perfect bond because the material model for steel is embedded into the cross-section. So the deformation between concrete and steel will be the same, which is essentially perfect bond. There is another way. We did some webinars on our website on how to use embedded rebars. I will talk about this one on the conference. But in this case, which is a more detailed kind of analysis, you can directly model rebars as beams, and you can embed them inside the concrete layers. When you do that, the beam and the concrete wall, they have different nodes, so you can create interactions between them. And one of these interactions can be, for example, bond slip. Now, since we are going to use as the more practical application of smeared rebars, I said, okay, let's do something. Let's create a new steel constitutive models that takes into account the bond slip effect, okay? Now, how can we do it? Let me see if I can annotate something. So I will explain you what we are going to do. Yeah. So we're going to create a material model, which is simply like a combination of a steel material model, let's say a simple elastic and strain hardening, kinematic strain hardening. We are going to do something like this. And we are going to create another material. So this one is stress and deformation on the steel rebar. We're going to combine this one with a material which is the bond slip, okay? And in my case, we are going to implement the bond slip from SEBFib model code, okay? fib model code 2010, which is a law, which is something like, so you have a tau and you have a sleep, which is a displacement. It has a sort of nonlinear strain hardening at the beginning up to a tau max, then a flat plateau, then it goes in softening, and then it has a residual plateau, okay? In cyclic behavior, it will be something like this. So with a pinching, and then it goes back here, and it does a residual plateau here in this way, okay? Now, the first problem that we will have is that this code here provides this law with tau, which is the tangential stress between the rebar and the concrete layer, and the displacement. So what we are going to do is we are going to convert this tau stress into an equivalent stress over the rebar, and the deformation and the displacement jump will be converted into a displacement, okay? So let me clear this one. So how we are going to do it? So just to recall a little bit the concept of sleep. So when they do test on sleep, they put a rebar, which has a sufficient anchorage length inside a piece of concrete, okay? So they put a force here. They measure the displacement of the rebar, which with respect to the concrete. So this one is going to be the sleep of the rebar with respect to the concrete. And what happens inside the concrete is that due to the shape of the rebar and the aggregates in concrete, there is a transfer of shear stresses from concrete to the rebar, which has, let's say, more or less a linear triangular distribution that little by little transfer stresses from the concrete to the rebar layers, okay? Up to a certain point, because at a certain point there will be slip, which means like a creation of cracks inside the concrete, and the bar cannot carry any increasing load. Now, by equilibrium, the force here, which is also equal to the stress in the steel times the area, the net area of the rebar, this one should be equal to the force onto the entire vertical surface, okay? It's here. It should be equal to the entire tangential forces, let's call it T, but this T is also equal to the tau times the vertical surface, which is twice pi the radius of the rebar times the effective length, which is the length of the embedment, okay? So the entire force generated by the tangential forces onto the lateral surface should be equal to the stress in the rebar, okay? So by simply taking this equation, we can convert the tau slip onto a stress strain equivalent constitutive model, and then we can put it in series with the steel model, okay? So this is what we are going to do in the code. Okay, after that, we are going to compile Opensees, okay? So just before I go ahead, do you have any question now? Or I can proceed with the source code?
Have you understand when you have to install CMake?
At the very beginning.
Okay.
Well, no, you can do it also now, just before compiling.
Okay.
It was not necessary to do it before.
Dependencies between
Visual
Intel
Studio and Intel, yeah.
only that.
Yeah, exactly. You were worried. Okay. Okay, that's fine. I will help you later on. So I think it's up to 4:30, then we will switch to the applicative example. Okay, so I will show you very quickly the source code, okay? So as I told you, by default, we are inside cohesive models, okay? Now in cohesive models, you just have an initial approximation of the complete source code. It's just an empty source code, okay? So if I open Visual Studio, I will show you how to code it. Well, it's not necessary that you use Visual Studio, but it's useful here. And this one. Okay, so I don't know how many of you are familiar with C++, but every time you do a new class in C++ or any new file, you typically need .h, which is an header file where you have the declaration of your class. And then the actual implementation is done in the CPP file, okay? So for example, here we are going to create a class which is called ASD Steel 1D Material, which derives from uniaxial material. So uniaxial material is the base class in Opensees for creating 1D material, 1D relationships, okay, where the strain and stresses are scalars. And then we have few things. I will go fast here because these assume some basic knowledge of C++, but if you don't have it, just try to understand what I put there, and then you will learn step by step. So the first things that you have here are related to the life cycles of this object. This is called the constructor, which is the first method called to create a new object. This one is the full constructor, which is a constructor that takes the same name of the class and takes all the input parameters. Then there is an empty constructor, which is basically when you don't put the input parameters and they will be given the default values. And then with this little tilde in front, this one is the destructor, which is who is responsible of deleting memory. Because one of the problems that you have in this kind of languages with respect to Python or other things is that you have to take care of memory. So when you allocate memory, you also have to deallocate it. It's not like Python. Then you have a few other stuff, like there is a method called getClassType, where basically you just need to return the name of the class. This one is the most important method. It's called, in Opensees, it's called setTrialStrain. It's a method that the finite element uses to set the deformation inside the material, okay? And the material is expected to get the deformation, compute the stresses, and the tangent modulus, okay? It doesn't give it as an output. It should give an output, an integer that says, for example, if it is 0, it means that the computation was fine. If it is minus than 0, it means something wrong happened in the computation. And so Opensees try to stop the analysis and reduce the time step if necessary. The first input is the strain. The second input is rarely used, but is the strain rate. Then you have a few other methods to get the current state. So give me the strain, give me the stress, give me the tangent, give me the initial tangent. These are just methods used to get data once they are computed here, okay? Then there are few data which are useful for nonlinear materials that are used for handling the current state. Now, when you have a nonlinear material, you know that, for example, the stress does not depend linearly on the strain. And to do that, they need internal variables that evolve with time. But probably you have seen that when you try to do a time step, the time step doesn't converge, you may want Opensees to restart that time step, for example, with a reduced time or with a different solver, as we have seen previously. When you do it, actually, you need to implement this one, because when something goes wrong in a time step, Opensees call revert to last commit. So go back to the previous converge state, and now we will start again from there. So these methods are very important. Otherwise, it will not be possible to restart an analysis at a time step in Opensees once you don't have convergence, okay? Then you have a few other things for getting copies. Send self and receive self. I'm not going to explain these ones, but they are needed for sending and receiving a copy of the material through different processors for parallel analysis, or for sending and receiving the material to a database, because Opensees has an opportunity to store an analysis on a file, and then you can start the analysis back from that point somewhere else, okay, on another computer, for example. But this method needs to be installed. Then there are another bunch of methods here used to update parameters. For example, if you want to change the settings of a material at runtime, or if you want to do parametric analysis, you may need this stuff here. And then the response stuff. This is everything is called by the Opensees recorders whenever you ask something. So for example, you have seen in the examples yesterday that you can use element recorders that, for example, I want to record the deformation inside every fiber of every beam. This is the method that is getting called, okay? So you have to implement them if you want to give some special output. So these one are the necessary methods that you need to implement. Then you can have some private method. I created some of them just for getting the output. Now, as I told you, we are going to create a material which is a combination of a steel rebar and a bond interface. So we may give the user the opportunity to get, of course, the total response in terms of stress and strain, but also the response of only the steel component, of only the bond component in terms of tau displacement, or the equivalent bond component in terms of equivalent stress and equivalent strain in the slip layer, the steel response here, and a few other stuff that are not interesting now. Okay, so once you declare all the method, you can declare the internal variables. So what do we need in this material? We need some parameters given from the user. So I try to keep them as few parameters as possible. So the user has to give the Young modulus of the steel, the yield strength of the steel, a kinematic hardening ratio. Then we need the concrete compressive strength, because the model code needs the concrete compressive strength to compute the bond slip ratio, the bond slip constitutive model. We also need the rebar diameter and the effective bond length, okay? If you remember, we need them to compute the equivalent scaling between the tau stress on the surface and the sigma on the rebar area. Then we need few data, the strain, the current strain, which is the trial one, the one that changes at every iteration, and the strain commit. Well, in Opensees, every time you see underscore commit something, it means that variables at the previous stage, which was the last converged value. A few other stuff, energy, if you want to compute the energy. And then we need the two actual material that will do the computation, which are two uniaxial materials, the steel material and the bond material, okay? Now, if we switch to the ASD CPP file, you will see the actual implementation. Now, for every function that I have here, I have a counterpart here. For example, the full constructor is here, okay? And there are rules. Now I cannot go into the details, but typically the full constructor takes the same parameters here. It initializes the base class and then copies the input parameters from the user to the internal variables, okay? And then here I said, okay, here you can do some extra initialization if you need it. Then there is the destructor. Oh, no, sorry, this one is the empty constructor. It says no need to do anything here. The internal variables are initialized to 0. There is the destructor. Now, in this case, I implemented the code because this is very dangerous if you don't do it. That's why I did it. Because since we allocated memory, we need to get rid of that memory. So once our material is going out of scope, we need to delete also this memory. Otherwise, we have the so-called memory leak. And this one is the most important part, set trial strain. Here is when we do the computation. So we start with an integer value equal to 0. We do our computation, and if everything goes fine, we return 0. Otherwise, we set up ret val, which is return value. We set it to an error code, like -1, for example. Once we are done, we just return the stress, we return the tangent, the initial tangent. Here, the default is that I return 0 because we need to change this code now. The strain, I return the strain that I have because I already declared it here. Then we need to do some stuff on all these other methods, okay? Now, I will not spend time on send self, receive self. They are not important, okay? Set parameter, I will not waste time, otherwise we'll run out of time. Set responses for the output is not interesting, okay? So I will focus on the main one. Now, coding everything now, it will take time. So what I will do is to simply switch to the new code, but here you can see the changes that I've done. So once you switch here, you will see that I have another commit on top of this one. If you go here, you will see the changes that I've done. As you can see, I did no changes on the header file because the header file was fine in that way. I simply made changes on the C++ file to implement the code, okay? So in red, you can see the things that I deleted, and in green, you can see the things that I added, okay? Now, I will try to go very quickly through them. Okay, so there is one method that I didn't explain it to you. Okay, so all the methods that are here are the implementation of these methods declared in the class. This one is a static method, and you will find a lot of them that starts with OPS underscore inside Opensees. It's a convention, but they are static methods used to convert the TCL or Python code that the user writes into the C++ code, okay? So when the user, for example, I decided, okay, my material should be something like this, uniaxial material, the name should be ASD still 1D, and then the user should give me some mandatory parameter, which is tag, ES, FY, and then I will explain everything about this one, plus the optional parameters. And this method is actually the method that is called by the TCL interpreter or by the Python interpreter whenever they find these two words. So uniaxial material ASD still 1D, go to this function. It goes here, and then at this point, it's my business to parse the TCL command line or the Python commands to see if all the inputs were properly given. And if everything is fine, I will construct that material, okay? For example, if the user gives me less argument, I launch this error, few arguments, and Opensees will stop, okay? And you will see the typical error, you made a mistake in creating a material. Okay, so here everything I did is to start with allocating the default values, okay? So everything set to 0, while the optional arguments are set to the default ones because they are not necessary. I mean, the user is not forced to input them. So the first thing that I do is to make sure to get all the mandatory variables, okay? So there are many functions in Opensees, but you can see, for example, this one is to get an integer. If it doesn't work, you return an error, and you do the same for all the data, okay? So I get the tag, I get the Young modulus, I get the strength, the hardening ratio, concrete strength, diameter, and effective length. At this point, you can see I don't do any check here. I must find them. If I don't get them, I throw an error. Now, up to this point, I can start parsing optional parameters. Now, since they are not mandatory, what I do is I start a loop until I have extra parameters from the command line. And if one of them matches one of my optional parameter, I parse them, okay? And I only throw errors if the parameters that they give me, they are not correct, okay? But they're not forced to give me those parameters. Just to give you an idea of what those parameters are, I go back here. It's a flag option for good bond or poor bond. This is required by the model code, because based on this parameter, the strength, the maximum tau will be higher or smaller. Now, one of the typical problems of the national codes is that they give you equations that are based on a specific unit system. In this case, the unit system should be in Newton millimeters. So since I don't want you to force doing your entire model in Newton millimeters, you can tell me what is in your unit system a millimeter and a Newton. For example, if I'm working in kilonewton meters, I pass minus mm, and here I pass 1 to the minus 3, minus n, 1 to the minus 3. So what is that unit in my unit system? And then a few other options. I want to compute the tangent matrix or the secant matrix, and I will talk about it later. Few other stuff for handling the softening regime, and I will talk about them in the example. Okay, so once you're done with everything, I ended parsing everything. Then I do some checks because you want to make sure not to create errors later on during the analysis. So you check, okay, for example, the Young modulus must be strictly positive. So you do a check here. If it doesn't pass the check, you throw an error. And you do the same for everything you think must be checked. Then you start creating the real stuff. So as I told you at the beginning, this material is not actually a new material. It's a combination of existing material. So what I'm doing here is to create an elastic, perfectly plastic material. I'm not going into the details of this one. Then I will create kinematic hardening material, and I will put them in parallel. So I have a linear elastic with strain hardening. At this point, I have my, where is it? Here, steel material. I allocated my steel material, and I'm fine with the first one. Then I need the bond material, because as I told you at the beginning, I need two materials, one for steel, one for bond. And here I'm just implementing the equation from model code. Okay, so if you go through model code, you go at page, I think, 230, you can find this equation. Okay, so I get the equation, I transform from the tau slip to the equivalent stress and bond strain, okay, according to the example that I give you before, okay? So I transform the slip to the slip displacement to the slip strain, the bond stress, the bond tau to the bond stress on the rebar, and I don't want any damage. Then I do some conversion. I'm not going into the details of this one, but what I'm getting here is a cyclic behavior following the FIB model code backbone curves. When I'm done, if everything up to here was fine, I'm able to create a new material, which is the ASD1. And so I pass all the settings that I parsed into this function, I pass them into the full constructor. So I have the tag of the material, the Young modulus of the steel, Fy, everything, but most importantly, the two instances of the two materials that I created, okay? An elastic, perfectly plastic material plus strain hardening, and a FIB model code pinching like material. Okay, so once I'm done, I just return the instance of the material, or if something went wrong, I throw an error. If everything is fine, this material is added to the domain in Opensees. And so the user keeps on taking this material, applying it to different components and so on. Now, I didn't do any change in the constructor. Okay, not change in the empty constructor. The destructor was the same. This one is the real method. Okay, so if you remember here, I just had do your own computation. Now, this method, as I told you, is the one that takes the deformation and computes the stresses and the tangent matrix, where the tangent matrix is the derivative of the stress with respect to the current strain. Okay, and what I want to do, the only thing I want to do is to impose. So the point is, I have two conditions to solve. I have two materials, so I have to compute the deformation in steel and the deformation in the bond in such a way that their sum is equal to the strain coming from the element, okay? And at the same time, I want the two materials to have the same stress. This is just the concept of two springs in series, okay? So I create a simple function, which is my nonlinear function, the one that I have to minimize, which is the isostress condition. This kind of thing here is a lambda in C++. If you don't know what it is, you can look into C++ documentation, but it's a function that can be declared inside another function. So this one takes some parameters, the trial slip value, because I want to compute the slip as a portion of my entire deformation. And I will update this slip until I find the condition of equal stress, okay? And as an output, I want the equal stress value, which is the one that I would like to be 0, and its derivative, because I need this one to compute the nonlinear iteration inside my material. Okay, so the simple thing that I do is that, okay, I assume that my steel strain is equal to the total strain minus the trial slip deformation. I assign this deformation to my materials. So here, what you see is that I'm imposing that the sum of the steel strain and the slip is equal to the total strain. I assign these two components to my two materials, and here they will do their own computation, okay? After they are done with their computation, I get their stresses, and I impose the isostress condition. So F is equal to the difference between them, and I want this one to be 0. Now, for the Newton-Raphson iteration to converge, I also need the derivatives of this function. And if you carry on the derivatives, you will see that they are just the sum of the two tangents of the two materials. So the derivative of the objective function with respect to the slip condition is the sum of the two tangent matrix from the two materials. And then I start actually. So this one is just a declaration of a function. I start with my initial guess. So the best initial guess that I can do is that my slip deformation is not changing from the previous step. Then I set up some settings, the maximum number of iteration, and the tolerances for the iteration, and then I say, okay, for the number of iteration, for an iteration starting from 0, less than the maximum number, increment this number, compute the isostress condition, compute the increment for the Newton-Raphson, which is the objective function divided by the tangent, update the current guess. Then before going to the next stage, I either check if the objective function is less than a certain tolerance, so if I met an isostress condition, or if I have no increment in the solution vector. So this one is like the Norman balance in Opensees and the norm displacement increment in Opensees is exactly the same thing, but I'm checking both of them. So if either one of them converged, for me, it's fine. If I cannot meet this criteria inside this loop, I will go out of my iteration loop without setting the convergent flag. So this means that I couldn't find the isostress condition because it's a nonlinear function, so it's not necessarily true that you can get it. And so you give an error. If you give -1, then Opensees will try to stop the current analyze command, and it's up to the user to either reduce the time step or change the solver or do whatever they want. Then the two other important stuff, get stress, get tangent. Now, if you know how two series work, I put a note here. The two materials are in series, so they have the same stress. So I can just return either the stress of the steel or the stress of the bond. They should be equal. But just for numerical round-off errors, and just because imposing the isostress condition is an iterative process, they may not be exactly equal. They will be equal under the desired tolerance that you choose. So I simply give an average. If my convergence criteria was perfect, then the average is equal to each one of them. Okay? Now the tangent. In two materials in series, the tangent is equal to the inverse of the sum of the compliances, of the sum of the tangents. So I simply do that. What I do here is 1 divided by 1 divided by the stiffness of steel plus 1 divided by the stiffness of bond. The only thing is that I put some guard against division by 0, because you cannot, when you code, you cannot just blindly code an equation, especially if you have division or square roots. You just have to do some, you have to take care about numerical errors. Okay, so I put some tolerances. For example, if one of the material has perfect plasticity and its tangent will be 0, I just replace it with a very small number. So just few numerical stuff, but the real important thing is this one. The initial tangent is the same, but instead of getting the get tangent, I get the get initial tangent. For the strain, I can give them my strain because I already imposed that my strain is equal to the sum of the two other strains, so there is no problem. The commit state is just a matter of saving the current strain, and it will be called when Opensees converges at certain time step. And the revert to last commit is the opposite, okay? So I restart my trial strain to the previous committed one. And I do the same in the two materials, because this material is a wrapper, so it's something that adapts to other materials to something else. So you always have to propagate this call to the submaterials. So same thing for revert to last commit. Revert to start is instead used by the Opensees command reset, because in Opensees, if you want to, instead of switching Opensees and running a new analysis, you can call reset and everything goes back to the beginning, okay? And then a few other things to get results, but this is not important, I think, for you, so I'm not going into the details of this one. So I would say we can have 10 minutes if you have a question or if you need help in the compilation stuff, but I don't know how many of you decided to compile. And then we will do the applicative lecture. It's from 4:30 to 5:30. I don't know if you want to do a break in between or not, and I don't think it's a break in there. Yeah. So if you have any question, we have 10 minutes now. I don't know if there are questions from the users.
Wow, still downloading and installing stuff.
Yeah, I imagine. It took me, it took me more than 1 hour to do all this stuff. So yes, that's why I was saying, well, I mean, you can try to follow these steps, and then you can contact me, or I don't know, how can we get in contact with them if they need help on this, because I don't think they will be able to do it in a couple of hours. Okay, so I mean, I was expecting this because compiling C++ is not easy. Okay, but this is the way if you want, you go into Opensees and you put new stuff. It's convenient because you can do several things from TCL and Python, but if you really want to add the new capability to Opensees, you need to code it, and you cannot do it through Python. Okay.
And what about compiling for Python?
Oh, yes, we need to compile. I forgot the most important thing. We need to compile. Okay, so in these 10 minutes, I did all this mess without compiling. Okay, so once you have done with the code, okay, so now we are inside build sequential, and we have this one. Okay, this is where we left. So you're done with the code, you need to compile. So so here you have all the lines you need for compiling Opensees and Opensees Spy. So the first line is to install the dependencies. That's why it's very convenient to use this approach instead of the plain Visual Studio approach, because with Visual Studio, you have to take care of there is a question, once the C++ framework, how to include it into an Opensees? I will show it to you right now. Then the second question, the way you show here in is for building a material model. How if we wanted to build a new element, it is similar. It is very similar actually, because as I created a new element, a new material that is derived from uniaxial material, you can do the same. You can create a new element which is derived from element. The concept is the same. You have to take the mandatory functions and you have to implement by yourself. The suggestion is that instead of starting from 0, you start from an element which is the most similar to the one you want to implement. Okay, so you have something already done and you can look at what the original author did to implement that model. And you can do the change only in the places where you need to change the behavior. Okay, but it's pretty much the same. It's not that difficult. Okay, so let's say once you are done with changing any kind of code, just the first time you need to install the dependencies. Dependencies are all the libraries needed to compile Opensees. For example, in the next hour, I will show you how to do an applicative example with STKO. And if you want your output from Opensees to be read in STKO, you will use the MPCO recorder. The MPCO recorder uses a database which uses the HDF5 library. Conan takes care of installing HDF5 and all the other dependencies for you, okay? So that's why this is very convenient. Now you can copy this one, or you can type it directly, and you can paste it here. Now, just a small side note for those of you who are going to copy paste one command at a time from PowerPoint. From some reason, Microsoft decided that when you copy a line, it also copies the last / command. So if you copy a line of command and the return character, it will automatically accept the command. Okay, so as soon as I paste it here, the command will run. Okay, so in my case, this command was very, very fast because it already found everything. So it found HDF5 and it found TCL because I already did it on my computer. In your computer, it may take few minutes, okay? But at the end of the day, it is finding zlib, which is a library for compression used by HDF5, TCL, the actual TCL required by Opensees, so you don't have to worry about the TCL version, HDF5, which is a library for this recorder I'm telling you, and Eigen, which is something else I'm not going to tell you. Okay, so this one will take few minutes, and you don't need to do this thing every time. Only the first time you compile every Opensees. Okay. In fact, in my case, it was super fast. It didn't do anything. Now the next step is to build Opensees. Okay. So actually, this one is the command they suggested, and this one works with Visual Studio 2019. Now, if I try to run this command, it will not work. You know why? Because if I call CMake, first of all, this command is actually used for CMake to prepare the Visual Studio files. It is not actually compiling. The compilation or the building happens here. This one is just setting up the environment for the compilation. So for example, it's saying that I want to build the BLAS library as a static. I want to use the math kernel library from the Intel. I want to use short integer and a few other stuff. But if you just use this command, it tries to get by default the latest compiler from Visual Studio. So it will get the compilers from 2022 and it will give you an error with the Intel. So the only thing that you need to do is this one that I forgot to put it inside the presentation. So I will put it now and I will share it to you on the chat. Let me go to the chat. So this one is the actual command that you have to run. If you see, there is only two minor changes. The first one is the \t v142. Oh, let me save this one so I can share it again after the lesson. So the -t option is to tell CMake that I want to select a certain toolset, which is not the default one, but the one from Visual Studio 2019. If you do this, this is fine, but then Conan library will complain about something. And to avoid this, you can just add this variable here, which is say, okay, Conan, I don't want to hear you. That's it, okay? So disable check compiler. If you do this one, everything will work. So I just copy this. By the way, if you already have Visual Studio 2019, you don't need to do this change. You can go with the default one. Oh, I have to copy this. Okay. Now it will take a little bit, like 2 or 3 minutes to set up the compilation, and then let's say 5 minutes for compiling. Okay, now let's wait. Unfortunately, compiling takes time. Yeah, so okay, so as you can see, it's trying to find all the libraries that are needed. Oh, and in this way, you will also have the MPCO recorder in Opensees Spy, because now by default, the Opensees Spy does not have the MPCO recorder. So you can use Opensees Spy to produce the output for STKO, and you can visualize the output inside STKO, even from an Opensees Spy model. Okay, once you're done, if you don't have any error, you will see build files have been written into your build folder. Well, the next step is to compile Opensees. Actually, you can do also the reverse. You can compile also Opensees Spy before and Opensees later on. It's the same. So I do the first one. This one will compile Opensees executable. I think I pressed enter twice, but it should not be a problem. Okay. This one will take a little bit more, like 5 minutes, so we can wait a little bit. In the meantime, if you have questions. We are about at 50%. Oh, and by default, when you compile it, I just use the default CMake build. This one will take all the available processors. So if you're doing something else on your computer and you don't want to waste all your CPU in compiling, you can actually specify the number of processors that you want, okay? But in my case, I just want to use all of them. Oh, by the way, it will take so much every time you start a new compilation from zero. But after that, for example, if you change just one line of code in one file, it will recompile only that file, okay? So it's not this long every time. Few more minutes and we should be done. Yeah.
any workloads we need to install for Visual Studio?
The payload, the work, it's called workload or payload.
Work.
I thought it was payload. Yes, the C++. So in the first tab, you have workload or payload, depending on.
Do you need Node.js? No.
No, not JS. If you want to develop some web application, I don't know. Yeah, by default, I think they give you Node.js for web development and .NET, but you don't. I mean, you need C++. And before going, I said, when you select the C++ workload, now you need to select the Visual Studio compilers for 2019.
343.
343 is the latest one. If you go on the right, you scroll down. So this one is the scroll down. 2019. This one, and put also the Windows from Windows side. Here, yeah. And the same that you found here, you can find it under individual components. You can find it. For example, if you type 2019, you can also find it here. Okay?
You can amend case.
But not the RAM, in that case, you need this one. Yeah. But I think you already have there, so it should be fine.
You can amend this stuff after you install that.
You can, because you open once again. Oh, just there was a question like,
I mean,
yes.
I
if
see
no,
better than one.
now there is a if you did it, if you installed Opensees and you forgot to set up the 2019, you can restart the Visual Studio setup and you press on modify, because it will find that you have Visual Studio 2022, modify, and there is, I think, add components. So you can choose it.
Also, this
Like, for example, if I show you, like in my case, if I run again the Visual Studio setup,
SDK,
yeah,
you can also amend SDK, right?
exactly. Now, for example, in my case, I already installed everything, but if I run again the Visual Studio setup, you wait just a little second, it will gather the information about your installation. It will say, okay, you already have Visual Studio, but you can modify it. If you modify it, you go back to the installation. So you can add either a new workload, or you can go to the extensions, or you can go to single components and you can type the Visual Studio 2019 building tools, and pay attention to the architecture, because your architecture is x64, x86, not the ARM, okay? So you can do it later on. I don't know, but I don't think so. By the way, so now we are done with Opensees, okay? So 3 minutes, almost 4 minutes. So it took this much because we compiled it from zero, okay? But as you can see now, I'm going to compile Opensees Spy, which is with this other command, and it will be super fast because actually almost 98% of the things that are required by Opensees Spy were already compiled by Opensees. So it will only compile few new files to compile Opensees Spy. So you take this one, copy here, and let's wait a few seconds. It will be super fast. As you can see, it's just compiling the PyDol modules and is linking, okay? Oh, by the way, every time you do a compilation, you have to look here. It will say how many things have been compiled, how many things failed, and the things that have been updated. The important thing is here, the failed stuff should be 0. Otherwise, it means something happened. And you go through the log here and try to understand what was the problem, okay? So now we have both opensees.exe and Opensees Spy, which actually is not called Opensees Spy at the beginning, it's called Opensees Spy.dll. And I'm going to show you where they are when you first compile them. They are going to be under, in our case, Opensees, build, sequential, because we are here, and under bin. Okay, so you have the executable for Opensees SYSL and the DLL for Opensees Spy. Now here, I added a few stuff to actually copy Opensees Spy into your own version of Python, the virtual environment, so we can test it. So for example, let's say I just compiled it, but I didn't copy it in my Opensees, okay? It will not work because it will not find my new material. So now what you can do is to first, now here I can clear, okay? First, I want to activate my virtual environment because I don't want to override the real Opensees Pi, okay? So I simply go to C, develop my Pi, scripts, activate.bat. Now I am in my Opensees Pi and I can copy this one. Okay, now if I copy this one, I'm just saying, okay, copy the DLL, which is called Opensees Pi, from the bin folder into the develop myPython lib site packages Opensees Pi win and replace the original one. Okay, but this is fine because I'm not doing it on the official one. I'm doing it on the copy. Okay, so I copy this one. Okay, yes, I want to override it. And there is one extra thing. As I think probably many of you have heard on the Facebook group probably that Opensees Pi was slower than Opensees STICL. I don't know if it was true or not, but in the default Opensees, you don't have this library. So it means that it has not been compiled with the Intel 1 API. So probably compiling with the Intel 1 API as the TCL one makes it faster. But anyway, you copy also this one because it's a dependency. Otherwise, your Opensees Pi will not start. So now you're here. If you run Opensees Pi here, you will find this new material. Now, just to show you why I decided to code this new material, and hopefully up to here, you will be able to compile everything. But in the things that I sent you in Opensees Days, course develop Opensees, you also have a few other stuff. Well, I also copied the two files for reference for you, so you can easily look at them into any text editor. I created two Python files. They are simple files for testing the new material. The first one is to use default materials with the standard series material in Opensees. If you run it, you will see that you have convergence problem. That's why I decided to create a new one. And this one is the actual file that will use my own material. Let me see, there is something in the chat. You cannot find it because either the system cannot find the path specified. So here you have the error. Now, there are two possibilities. Either you didn't compile Opensees Pi, so it is not finding bin Opensees Pi, or you didn't install myPy. Okay, so it is not finding the right-hand side. So try to see what of these two files are missing, either the Opensees Pi or the myPy lib site packages folder. One of these two things were missing, okay? But I think you didn't compile it because otherwise you were too fast. Try to see. I think it's the first option, but have a look. Anyway, there you can see the test file. The test file is very easy. So I do the typical thing of importing stuff. I define the user settings that you can do. For example, I decided to have a stand. Well, here I'm modeling in Newton millimeters. So I have the standard 200 megapascal young modules of steel, 200,000 megapascal, 400 megapascal of yield strength, 0.2% of strain hardening. The concrete, which is about 25. I don't have good bond because I put an extra backslash at the end, bottom slash at the end, so it's not activating the good bond. I'm saying that the effective length, so the anchorage length is 200 millimeters. The diameter of the rebar is 10. And I don't want these options. So that's why I put some things here. So they will not be recognized. Then I decide I want to test it under a cyclic behavior. And this thing from Portwood Digital, which is the blog post of Professor Scott, is very interesting. It suggests you to use a white noise, a random input to test your material, because when you apply a random input, there are high chances that you go inside every piece of your code. So it's easy, it's better for debugging. And then I do a few stuffs. I start a new model, wipe model 1D, 1DOF, because I just need to test a 1D material. So I create a DOF with 1D. I create the uniaxial material with all the settings that we said. Then I create a unit length truss element. That's it, with a unit area. So the displacement that I have is equal to the strain, and the reaction that I have is equal to the stress, nothing but that. I fix the first DOF, so I have only one DOF free. And on this dov free, I actually apply an imposed displacement. Okay, so at the end of the day, I have 0 free dovs. And the displacement will be controlled by a time series, which is equal to the noise, to the input noise that I assigned. Then I do a few stuff to plot the results in real time in Matplotlib. So I'm not going into the details of this thing, okay? It's just Python and Matplotlib. So if you are here, you activated your own Python. Now I go into this folder. Okay, now I'm here and I want to run the proto new material. Well, proto stands for prototyping. So Python proto new material, and it should give you an output like this. So on top, you will see the strain history that I'm giving. Then on the right-hand side, you have the still response. On the bottom of the right-hand side, you have the sleep response. And here you have the combined response. So the still with the bar sleep. So you have a different initial stiffness, because at the beginning, the still was stronger, was actually weaker than the bond strength, but the bond strength was going into strain hardening, as you can see here, okay? So it was actually changing the initial slope of the steel. But at a certain, so the slip was, the steel was failing at the beginning. It was failing in plasticity, but since it has strain hardening, it was managing to carry increasing load up to a certain point where it hit the plateau of the slip. And at this point, you have the slip condition, okay? So you see this softening here, which corresponds to the slip. So it's like you're pulling the rebar, it's plastifying, but then you have strain hardening, and at a certain point, the concrete at the sides of the steel is failing, and so the bar is slipping from there. And at that point, you have this strain softening behavior, okay? Oh, by the way, I think at the end of this file, you have something which is commented. If you want, this one is used, I typically use it for storing this animation in Matplotlib into a GIF file. So it's useful for animations when you want to create documentations and stuff. You can simply uncomment it and it will save the animation that you just done into a GIF file. Okay, so if you don't have question about this, we can go to the actual example in STKO, okay? Or if you want to take a small break, I don't know. Okay, so let's see. Okay, we don't have questions, so we can start with STKO. So in the example with STKO, the folder is this other one, course, applicative example, shear wall STKO. You have a small PDF file, which is couple of slides from a thesis of which I use as a reference for this benchmark, okay? Here we are going to test the unit 1. So here you have all the dimensions in millimeters. Unit 1 is this one. So we have 2 boundary columns and the internal shear wall, which has only 1 layer of grid reinforcement in the middle, okay? For simplicity, we are not going to model the bottom beam. We are not interested in that detail. We are just going to model everything as a shell, okay? On top, you just have a stiff beam, but nothing special. So this one is loaded as a cantilever, okay? Only on one side, but this one is stiff, so I will put an imposed displacement in the middle on top. And there is somewhere, yeah, the details of the materials you can find here, the loading protocol, the real loading protocol, and then some output, so we can see what happens, okay? Okay, let's go soon to STKO. And you can open this file, by the way, okay? Now, the file is already done, so I will try to explain you how it works, how I did it, and I will try to go step by step, okay? Okay. So well, first of all, I decided to model everything with shell elements. So, well, just a brief introduction to STKO, by the way, because probably you didn't know about it. So it's a pre and post processor for Opensees. You can switch from the preprocessor to the post processor here. In the preprocessor, you have, well, the different commands here for building the geometry and doing all the assignments, but I will go through the work tree because it explains it better. Up to here, So you have work plane, local axis, few stuff. Selection set are just some selections, but the two important things are here, geometries and interaction. So up to here is not Opensees, you're just doing a CAD modeling, okay? So for example, in my model, I just need a multi surface, okay? Which is, let's say, a combination of surfaces attached together on edges, okay? Why I need them? Well, because I need two separated surfaces here and here, because they need a different material property for the two different boundary columns. And then I need two surfaces in the middle for the shear wall, because it has a different material. So why did I model them split in two? Well, because I just need a vertex in the middle to apply the horizontal displacement, okay? How can you model this one? Now this one is already done, but I will show you very briefly how you can do it. So you draw your lines here, whatever you want, okay? Then you do your construction. Let's say you want to do something like this, something like this. Okay, once you have your wireframe modeled, you can go with planar surface, you select all of them, right click, cancel, and you delete the boundary lines, okay? So you now have a single geometry made of, in this case, 3 faces. Okay, if you want, you can get rid of some of them, you can do some modification. If you forgot something at the beginning, you can draw them later on. You have Boolean operations, okay? Not like this. Like this, okay? Then you can get rid of something, so you can play with it, okay? It's just a CAD model at this point. So once you're done with the geometry, there are interactions. Interactions are typically used and are not used in this example, but they are used when you want to apply a kinematic constraint between two objects, or you want to create contact. For example, imagine I have a node here, which is the master node of a diaphragm, and these one are the other beams in the diaphragm. You can simply create an interaction like this, select the master node, select the slave nodes, and you have an interaction. And on top of that, okay, on top of that, you can assign the boundary condition, okay? But in this case, the model is pretty simple and we don't have any interactions because everything is modeled inside this surface. Okay, so once you're done modeling, from definition down to analysis steps, this one is the interface between STKO and Opensees. So you will find all. How do you download STKO software? You're right, but did they receive also the coupon, the one that are online? I think no, because they are, but they can be sent probably. Each one of them can be sent one of those codes probably. Okay.
I don't know.
You just go on our website. Hopefully I can get through it here. ASDIAsoft. Let me see. Well, I need, but you just type ASDIAsoft on the web and you will find it. Now I'm not under VPN. Okay, so probably you will not be able to find it.
Directly with your
Sorry?
try directly with your URL. maybe
Let
it's
me see, but I don't
not
think.
Google.
Oh, it's going, yes. So it's just Google that is not working. So, okay. So when you go here, you go to download, purchase STKO. Now, in your case, you go to download STKO. Before doing this, you need to create an account, okay? Once you create an account, you can download STKO. You can follow all these instructions, okay? You activate the license and you will have a free 30 days license. Then you can send us the code. There are the instructions on the coupon here. Since you attended this course, you will be able to extend the license for free to 1 year, okay? Now, since the coupon were physically given by to the attendees here, I think we can ask the coordinator, someone, to send you to send each one of you online one code of the coupon, okay? So I will talk with them. Okay, so no, we actually give them the coupon to the committee down here, but we give them physically. So we didn't think about the guys online. So we can send them some of those codes. Yeah, we will discuss them in the next days, okay? But in the meantime, you can download it and you have 30 days trial. So we will take care of that. Okay, so so what I said, from here down to the bottom is the connection between STKO and Opensees. Just a reminder, STKO doesn't have Opensees inside. So STKO is just a user interface, pre and post processor. It's up to you to have Opensees, and you must tell STKO where to find for Opensees. And you can have different versions of Opensees. For example, I have some official ones and some developed ones. Okay, so you can load them. Everything here is given on the documentation, so I'm not going to repeat everything. And then you can switch between one solver and the other. Okay, but the important thing is that if you only have STKO without any Opensees, you can do the modeling, but you cannot run analysis. Okay. So from definition down to analysis steps, you have the connection between STKO and Opensees. So for example, under definition, you have the most used thing, which is the time series. So every time you want to create a new thing, you right click on top of one of these top nodes. For example, I want to create a new definition. You go here, add, and you choose a model. In this case, under definition, we have the time series, random variables, limit curves, few other stuff, but we need time series in this case. Now I already created them, but every time you choose a new one, for example, I choose a constant time series, it goes to the settings that I have for Opensees. As you can see, I use the same name, same things, and there is also a link to the Opensees documentation. So if you don't know what that stuff is, you click here and it should send you exactly to the Opensees documentation, okay? Okay, so I already created some of them. What we need is a linear time series, and the linear time series is used for applying the vertical. So what I do, it will be a first stage where you apply a gravity load, and this one should be done in a monotonic way. And whenever you have to add the load in a monotonic way, you have a linear time series. So it goes from 0 to 1, which is at time equal to 1, I have 100% of my load applied. Then I need a cyclic time series for applying the displacement. Now I created two of them. This one is the real one taken from the paper, okay? But for reasons of speed, I want to make the analysis faster. So as you can see, for each amplitude, I think we have 2 or 3 cycles. So instead of having all of them, I created a reduced version of it just for this example, okay? So I took just one cycle plus minus for every amplitude. I'm going to use this one, but if you want to use the real one when you're redoing this example at home, I mean, use the other. So once you're done with the definition, you need to define new materials, okay? Now this one is the one for steel bond, but I will talk about it later, okay? So let's start by the three-dimensional material for concrete. Now, every time you need to create a new material in Opensees, or in STKO actually in this case, you will find them under physical properties. In physical properties, you are defining everything that defines the constitutive behavior of your model, which are basically materials, sections, and other special purpose stuff, okay? I will talk about them later. Material, you can have uniaxial material or ND material. Now, for example, if I want to create, I don't know, a steel material using the standard steel 02, I can find it here, steel and reinforcing steel, steel 02 material. Now, the nice thing about the material definition in STKO is that you can test it before you use Opensees. So for example, I want a material and let's test it with these settings. So in megapascal, let's say 400 megapascal of strength, 19, 0.925. Let's set by the default parameters. And let's put, for example, a 0 strain hardening. And then I want to test it with a 10 cycle of asymmetric linear increasing protocol up to a deformation of 0.04, okay? You test it and you have your output, okay? So let's see what happens if I put 10 here, because let's say I don't know what this parameter means. So I test it and I can see that it affects the cyclic behavior of this one, okay? So I bring it back, I don't know, to 19. So I say, okay, but I don't want it to be this flat. I want to add some strain hardening. You say you put 0.1, no, it's too much, okay, and you lower it. So you can play with it. It's a nice way to play with parameters, okay? Now, I already created some of them. So I created the AST Concrete 3D, which is a three-dimensional material model for concrete that we implemented in Opensees recently, and I will talk about this at the conference, okay? But it's a simple constitutive model for concrete in 3 dimensions. Then I created a uniaxial material for steel, and I will talk about it at the end. Okay, now let's give it for good now. Now that you have a uniaxial material for your rebars, what you have to do is to convert the uniaxial material into an equivalent smeared layer, a three-dimensional smeared layer, okay? And for doing that, there is a tool in Opensees, which is under material ND, other ND material. It's called plate fiber. Where is it? Plate fiber material. Or no, so it's, yeah, it's the plate rebar. So it should be under material ND, materials for modeling. Exactly, this one, plate rebar. So this one is a wrapper. So every time I talk about wrapper, I talk about a material that changes the material of the behavior of another material. So this wrapper takes a uniaxial material as an input, which is, for example, the uniaxial material for steel, and it transforms it into a layer of shell into a certain orientation. For example, 0 means that my material is aligned with the local axis, okay? So it's like this one. This one is the default local axis, the X local axis of my shell, and this one is the angle of my rebar, okay? So if alpha is equal to 0, it means my rebar is horizontal. If I put 90, because it's in degrees, it will be vertical, okay? And you can put any number in between. So I have the 6 diameter rebar in the middle, which have an angle of 0, and a 90-degree rebar with the same material. Okay, so I put 90 here. These two layers will be used for the inner part of the rebar. The one at 0 degrees will be used also here on the columns, because the inner grid goes into the column. But then I need another one, which is instead for a material of a higher diameter, which is used for the vertical columns, okay? So I create another one of them with 90 degrees inclination, which means vertical. Okay, so once you're done creating the concrete and the steel materials, all you need to do is to put them into a composite section, because as you can see here, I have only one layer, okay? But for the shells, you can do the same thing that you did for the beams. So you can have a fiber cross section, okay? So it's up to 530 or 430. It's 5 or 530, I think 530, 530. Okay. So the shell can have, whenever you have to create a composite cross sections for shell, it's like for beams. So, but instead of having fibers in 2 dimensions, you have just a line of fibers along the z-axis, which is along the out of plane axis, okay? And you can do this with the section layer shell. In the section layer shell, which is under sections layer shell, you can define any list of materials. Like in my case, I want 1 layer of concrete on one side, 1 layer of concrete on the other side. I just need 2 layers of concrete. I don't need more materials, because in this case, I'm just analyzing the in-plane behavior. But if you want to analyze also the out-of-plane behavior, you may need other fibers, okay? So each one of them will be given half the thickness of the entire wall. And then here you can put the other rebars. I have 1 layer in the middle oriented in the 0 direction, so horizontal rebars, and 2 layers at 90 degrees. Why did I do that? And instead of just having 2 layers of 0 and 90, because in that case, the section would be non-symmetrical. So I would experience some out of plane bending and instability. So I simply assign 1 layer in the middle in one direction, and in the other direction, I apply 2 of them, and they will assign half the thickness. So the important thing is that you have the same amount of steel. So on the first layer, on the first point here, you assign all the layers in terms of material. And here you have the same numbers, but in terms of thickness. So my total wall thickness was 0.1 meters, okay? So I put half here and half here. So these two will give me the total thickness of the wall. And here it is very important that you put an equivalent thickness. And how can you compute it? This one will be equal to the area of that rebar divided by the spacing, okay? So in such a way that if you multiply this thickness times the spacing, you have the area of all the rebars in that portion, okay? So it's just an equivalent thickness that gives you the same amount of steel. So it is very important that you compute it properly. Okay, so once you're done, well, I do the same for, and this one is assigned to, oh, let me go to properties. So you see the properties here. So this one is assigned in the middle because I only assigned, as you can see here, the 6 diameter rebars. While on the columns here, you can see that I have something different. Okay, different thicknesses because the column is now 0.2, is thicker than, where is it? It's thicker than the wall, which is this one. And it has a different layout of rebars, okay? So when you go here, you will find that I have one layer of horizontal rebars, the one that I told you that go inside from the wall inside the columns, and then 2 layers of vertical rebars with a different diameter, which is the diameter of the strong columns, okay? And then the usual 2 layers of concrete. Now, on top of that, you have the rectangular cross section, just an elastic section to make a stiff top section. Okay, so up to here, you're done with the physical properties. Then you need to assign the finite element models. So we have a shell. This is the ASD shell Q4 that we developed, but you can use any other type of shell. You will see that the shell MITC4 has some problems, so you can either use this one or the shell DKGQ from Professor Lu. There are differences, but there are differences in the bending behavior. In the in-plane behavior, they're pretty much the same, so it's not a problem. And you need a finite element for the top beam, okay? Just an elastic beam column element, nothing more. Then you need to apply boundary conditions, okay? So what I need to is to apply a fixity at the base. And also here, when you go to boundary condition, you go under model and you choose what you want. It can be a constraint, single point or multi-point constraint, ground motion, loads, masses, okay? So what are the constraints they applied here? A fixity at the base. So I select the edges here, down here, and I say the entire base should be, it's a 3-dimensional model with 6 degrees of freedom, displacement and rotation, and I want to fix X and Y and the drilling rotation here, okay? These 3 out-of-plane degrees of freedom will be fixed everywhere instead because I'm using a 3-dimensional shell, but I want to do a 2-dimensional analysis, okay? So I select my entire model and I fix the out-of-plane degrees of freedom. Then I need to apply vertical loads. So I have, in this case, I have on this surface, a distributed load for shells. And this is one of the tools for which SDKO can be useful. For example, in Opensees, you don't have distributed forces or distributed couples on surfaces or volumes. So what we do is to create an automation where the user can apply a distributed load as a force, for example, and then SDKO automatically converts this one into equivalent nodal loads, okay? Because it has a mesh, and I will talk about the mesh later. So it does the proper conversion for you, okay? You can also give them as function. You can give them in different local axes, so you can play with them. In this case, I want a total force which is equal to the self-weight times the thickness. So 25 kilonewton per meter cube times 0.1 meters. So I have minus 2.5. And here on the lateral column, it's the same, but the thickness is twice as that, okay? And then I have the self-weight of the top beam. In this case, it is a beam, it's an edge load, so it's a self-weight times an area, okay? Okay, once you are done with that, I want to apply the horizontal load, which is an imposed displacement on this node, okay? And I give it a value of 1, because actually I will use the time series that I defined at the beginning, which has the real displacement. So the time series times the imposed displacement of 1 will be equal to the total imposed displacement, okay? So it's up to you. You can either put the final reference value here, and then you normalize the time series, or you normalize the reference load and you put the real value in the time series. The important thing is that the product between the time series and the reference value is the value that you want. Okay, so once you're done with this, you defined all the conditions, but you didn't tell Opensees in which order they are applied, okay? So you just define them. So the next thing is to go into the analysis step. Here is where you define your, it's like how you write all the things that you defined before into the TCOL file. So for example, the first thing that I want into my TCOL file is the, well, after of course the nodes, the elements and everything. I want the recorder. And in my case, I will use the MPCO recorder, which is, instead of giving you different files for each result, which is fine in certain cases, but not useful in others, for example, for visualization, it saves everything you need into a single database. Okay, so everything you need to decide is the name of the output file and the results that you want. For example, on nodes, I want to store displacement and reaction forces. On elements, I want to store section force and deformation. Fibers, I want to save stress, strain, and damage on fibers, the crack width on every fiber. And as you know, in Opensees, while the nodal results are very well known, there is a fixed number of nodal results. The results on element can change based on the element type, because it's up to the developer of the finite element to decide what kind of element what kind of result you want. So for example, in my case, for a shell, I can ask any result on section fiber, which means on every fiber of every section. And since I'm using the ASD Concrete 3D, I'm also providing a result, which is the crack pattern and the crash pattern. It will give me where the concrete has cracked in tension or crashed in compression and the direction of the crack and crash plane, okay? So you can also input custom results. Then you have a record frequency. For example, if you don't want to waste too much time and memory, you can say, okay, I don't want to record every time step. I want to record every 20 steps, for example. Also, if you want to reduce the size of your model, you can decide not to record onto the entire model, but only some subsets. So you can create regions and you can put them here. Now, in our case, the model is pretty small, so I would record everything. So after this, the first thing that you need are the boundary conditions. We just have two fixities, fixed base and fixed out of plane. For some reason, I left one multi-point constraint, but there is nothing because we don't have multi-point constraint here. Okay, so up to this point, I have the recorder, I have I have single point constraints. Then I need to apply gravity loads. Okay, so I create a pattern, add pattern, because you can also remove a pattern, of course. And I want to add the load pattern. Now, a load pattern requires a time series tag, as you have seen in the previous examples, where you just assign the load multipliers for the loads in that pattern. So the first pattern is for gravity loads, so I need a linear ramp. And the gravity loads are three: self-weight on the web, self-weight on the boundary columns, and self-weight on the top beam. And then you run the gravity analysis. I just choose a static analysis transformation method for the constraints, RCM for the number, UMF pack, I want to use a sparse solver, Krylov-Newton, and a few other settings. In my case, I'm using the norm displacement increment. 1 to the -5 is fine because I'm modeling in meters. And unload control, and this is another nice tool that we have in STKO. You can use adaptive time stepping. So if the analysis is not converging, STKO writes a particular scripts for reducing the time step if you don't reach convergence, or increasing the time step if you are converging well. Anyway, this one is the gravity analysis. I do not expect too many nonlinearities, so I try to solve it with just one step. After that, I want to keep the gravity load constants, and I want to reset the pseudo time step to 0. And I clear the analysis settings. So up to this point, I will be done with the gravity analysis. Here, all I have to do is to apply instead now the horizontal loads, which is a new pattern. In this new pattern, I apply the time series. And the time series will be the cyclic one. Now you can use either the full cyclic or the reduced cyclic. Now I want to be fast in this example, so I will use the reduced one. And now the load is an imposed displacement, so it doesn't go under load or LA load, but it goes under SP, okay? So it's here, it's a push load. Okay, once you're done, you can go with the analysis. But before that, I put another automation that we have in STKO. I want to monitor a result in real time, okay? So what I did is to create two selection sets. One for the control node on top, because I want to monitor in real time the displacement of that node. And I want to monitor the reaction at the base, okay? So I create another selection set with all the edges at the base. Then I create a monitor, and in this monitor, I give it a name, and I say that in the x-axis, I want to record the displacement on the control node. I want to multiply it by 1000 because I want them in millimeters. And in the reaction forces, I monitor the reaction force always at the top, because actually I'm imposing a displacement. So at that point, I will also have a reaction. And I want to compare it with experimental results. So here I put the points extrapolated from the thesis of the experimental result, okay? Since they were given in kilonewton millimeters, I put also here the units. And finally, the analysis. Same settings as before. I just use more time steps because I need it for convergency, okay? Now, just a side note before running the analysis is for the steel material. Now, when you create a new material, which was not in Opensees before, STKO doesn't know about it, okay? So it doesn't have a tool to interface with that new material. So for that reason, we have the default, which is the custom material. The custom material doesn't know what material it is, so it gives you the opportunity to define the class name. It's up to you to put a valid class name and a list of parameters in the correct order. So for example, the first parameter I was expecting was the initial stiffness of steel, the yield strength of steel, hardening ratio, strength of concrete, and few other stuff, okay? I won't go into the details of this one because we are running out of time. I'm just trying to, I will do a test here, by the way. So monotonic. Okay, so this one is the output that I have for my material in monotonic state, okay? So let's see what it looks like. If I take this one, I open Excel and I want to compare it with something else. So this one is my material, which is the result of steel and bond. As you can see, it starts with the stiffness of steel, as far as the steel is softer than slip. Then up to this point, due to the curvature of the law of the bond slip will be weaker, so it will win, okay, up to this point. Then there is the yielding of steel. The steel will progressively increase the strength up to the point where it will be higher than the bond slip, and then there will be slipping, okay? Now, for example, since you know that the bond slip law is governed by the strength of concrete, let's see what happens, for example, if I go here and I say, okay, no, my concrete is not 25 megapascal, but is 1,000 times higher. So basically here I'm expecting to see just the behavior of steel, because now the bond will never be activated because I exaggerated its strength, okay? So for example, here, if I add new data, okay, you will see exactly the behavior of steel. So this is what the bond was doing at the beginning, okay? Okay, now let's go back to the default settings and try to run the analysis. Let me go back to the real strength of concrete. Okay, save. The last thing that you need to do before running the analysis is the mesh. So you go here, you decide the size of your mesh. In my case, I want uniform by size, 0.4 meters. Okay, very coarse, but just for doing something very fast, and you run it. Okay, you choose the folder where you want to run it. Now it will start the analysis and it will create the monitor here. Now here it will start monitoring, so you can see how it is performing with respect to the experimental setup. Now I already calibrated the parameters, so it's going fine. It will not do the last cycles just because I'm using the reduced number of cycles, but it's pretty fast. Now, if you're wondering why you're having a constantly two iteration, is because I'm using a particular integration scheme in the material, which is called Implex, and it's an integration scheme that guarantees convergence in just 2 steps in every nonlinear analysis, but I don't have time to explain it now, so I will talk about it during the course, during the Opensees conference, okay? So with this one, you're done with the analysis, less than 1 minute here. Once you're done, you will find the results here, okay, under the name that you give it. So Mastianic shear wall results.mpco. So once you're done with that, you can open the file. Okay, so by default, when you open a file, you will find a default plot. Okay, so in STKO, you can create different plot and plot groups. So you can create also different plots, one next to the other, to do some comparison. Okay, so if you want to visualize the displacement, you can look at these ones. Okay, so you can go here, do the animation. You can change the type of results that you want to see. You can change the deformation scale. Okay, so you can play with it a little bit. Now, I don't have time to go through all the details. I will show you just the crack pattern that can be interesting for this example. The crack pattern was this result here. It's given by 9 components and it's giving you the 3 most open cracks inside the shell. You will see it as a cylinder because in 3 dimension, I need to define a plane. So it will show a cylinder which is on the plane of the crack and it's extruded in the orthogonal direction of the crack. The color and the extrusion of the cylinder will be proportional to the crack width. So for example, here I have 5 millimeter crack width at 45 degrees, okay? And also here you can do an animation to see how the crack width is working, okay? So at the beginning you have the typical, let's go here to the results. During the first cycles, this one is a kind of result between mix between bending and shear. And at the end, it fails in shear. So at the beginning, you have these diagonal cracks quite distributed on the columns. You can see it from here on the different columns, which are basically this one that you are visualizing now. Okay, so these initial cracks, then it's done in cycles. And up to a higher displacement, you will see the opening of the 2 main diagonal cracks, okay? Of course, if you want to see a complete failure, you may want to rerun this analysis with a finer mesh. You will see better results, okay? But I think, we have some more minutes. So just to show you, for example, what it looks like when you go through a more detailed model, and the crack plot can be very useful to visualize this kind of things, is what I will show tomorrow, not tomorrow, the day after tomorrow, actually, at the conference. Let me see. Okay, so this one is let me see if I can run it from here. Okay, so of course, if you use a finer mesh and different ways for embedding rebars inside that, you can have a more detailed result of what's going on. But even a very coarse mesh, like the one that I showed you before, can give you quite good results. Okay, so I think we have some time for questions, or if you need any help in compiling. Okay, thank you. Yeah. Yeah, I was pretty fast on that. So once you did everything, so for example, first the geometry, which is this set here, then the interaction, we don't have them, property, boundary conditions, then you have the analysis settings, then you do the mesh, and at the end of the day, you have to run the analysis. Now, running the analysis actually first writes the input file, which are TCOL. In fact, if you go into the folder that I created here, which is course applicative example, you will see a bunch of TCOL files, okay? There is a main TCOL file. Open it. Okay, there is a main TCOL file that opens all the other TCOL files, definition, material, section, nodes, elements, and analysis steps. And they are basically the copies of these things. You can either do it with write input file or run analysis. But run analysis does first the TCOL file, and then it calls the default solver that you have here, okay? So it basically creates a batch file that say, okay, run the selected solver with the main file that you have in this folder, okay? That's it. Of course, to do this, you need to set up a solver. You need to have Opensees installed, okay? And the first thing that you need typically when you install the first time Opensees is to find a solver in your computer, okay? And you can do it through here, for example, import solver, and you find the solver that you need, okay? And yeah, it will automatically set up it for you, but basically it's the name of the solver, then this placeholder, which will be replaced by the name of the file, okay? But you will find all this information on the documentation. Welcome. There are questions? I did it. Finito. Yeah. Is a steel fiber reinforced concrete model already implemented in Opensees? Is there the possibility to predict cracks opening as per the example just shown? This one actually, I don't know what you mean by steel fiber reinforced concrete, because what I'm using here is one material for concrete, which is already implemented in Opensees. I know just fiber, but you mean a fiber that takes into account both concrete and steel? Or as I show you here, because here I show you a fiber cross-section, layer cross-section in this case, where some fibers are made of concrete and some fibers are made of steel, okay? And the section will give the combined results. So this one, yes, they are already in Opensees. The concrete, SD Concrete 3D is already in Opensees. This steel material here is not in Opensees because we just developed it now, but you can replace it with any other steel. So you can go here, you can go under material, uniaxial, steel, and reinforced steel, and you can replace it with one of the steel materials that are in Opensees, okay? And yes, you can use it for predicting the kind of failure as I did here, okay? So these materials are already inside Opensees. The only one that is not in Opensees is this custom material, because we just developed it now. By the way, I will upload it to Opensees in the next days, okay? So it will be on the official Opensees repository soon. But if you want to test it now and you don't have this material because you didn't compile it, just use another material. For example, how can I set the kind of steel fiber like type 4C, etc.? You just go here. So you edit this one, edit. You have to choose a different model. So you go under material. It should be a uniaxial model, and then you can change it whatever you want. So for example, typically you should go under steel and reinforcing steel, and you can choose the simplest steel 01, steel 02, steel 03. I don't know what you mean by type 4C, but I think steel 4 probably. Anyway, you can choose any of these material. For example, steel 01, you just have to choose the Young modulus, the strength, and the hardening ratio. Okay? So you can just change the model and change the parameters accordingly. Okay? Is there any other question? Can you please show the option to define the crack pattern in the visualization again? Yes. So, well, the first thing that you have to do is to request that result, okay? And the result is called crack pattern and is inside the ASD Concrete 3D. So pay attention that these results is available only for this concrete model, unless someone else will implement it also for others. And since I'm using this three-dimensional model into a section for shells in every fiber, I need to tell MPCO that I need these results in every fiber of every section, okay? So once you have this result, you run the analysis, you go here and you create a crack plot. So you have different kind of plots here or here. You need a crack plot, because if you choose the default surface plot, which is used to visualize scalar values, you can still see, actually you cannot see it here. You can see it in the fiber plot, which is used to visualize all the fibers, okay? But if you look at here at the crack pattern, for example, you can see the different components. Like the first crack, you can see the X component, Y component, Z component, but it's not meaningful in this case. So the crack pattern is useful in the crack plot, which understands the kinds of results and shows you, instead of the single values, the entire crack plot, okay? So right click, crack plot. Okay. So I think it's fine. If there are no other questions, thank you. Thank you very much.